If you like the space and learn about its curiosities, consider subscribing to the channel. Thank you for your attention and enjoy the video. In the vast and unfathomable depths of space, black holes stand as some of the most mysterious and captivating objects known to humankind. They defy our understanding of physics, challenge our perceptions of reality, and evoke questions about the very fabric of the universe. Black holes are often described as cosmic monsters, consuming everything that comes too close, but their true nature is far more complex and awe-inspiring. These massive objects are regions of space where gravity is so intense that not even light can escape, making them invisible to the naked eye. Scientists have discovered various types of black holes, from small stellar black holes to supermassive giants that sit at the centers of galaxies, including our own Milky Way. Yet, many mysteries remain. One of the most profound mysteries of black holes is the nature of their singularity. At the core of a black hole lies a region where all known laws of physics break down, known as the singularity. Here, matter is compressed to infinite density, and the concepts of time and space become meaningless. What truly happens within this singularity is unknown, as no information can escape from within a black hole's event horizon. Some theories suggest that black holes could be portals to other parts of the universe, or even to different universes entirely. This idea, while speculative, has captivated both scientists and science fiction writers alike, raising the tantalizing possibility that black holes could be gateways to new realms of existence. Another enigma surrounding black holes is the so-called information paradox. According to the principles of quantum mechanics, information about the physical state of a system should never be lost. However, when matter falls into a black hole, it appears to vanish completely, leading to the paradox of whether information is truly lost forever. Stephen Hawking famously proposed that black holes might emit radiation, now known as Hawking radiation, which could, over incredibly long periods, lead to the black hole evaporating. This process might theoretically allow information to be released back into the universe, though in a highly scrambled form. The debate around the information paradox continues to be one of the most intense in modern theoretical physics. Supermassive black holes, often millions or even billions of times more massive than our Sun, are another cosmic wonder. These enormous black holes reside at the centers of most galaxies, including our own Milky Way, where one called Sagittarius A** quietly lurks. The origins of these supermassive black holes are still uncertain. Did they form from massive clouds of gas that collapsed early in the universe's history, or did they grow gradually as smaller black holes merged and consumed surrounding matter? Answering this question could reveal essential details about galaxy formation and evolution. In recent years, technology has granted us glimpses into the elusive world of black holes like never before. In 2019, humanity witnessed the first ever image of a black hole, captured by the Event Horizon Telescope (EHT). This groundbreaking achievement showed the silhouette of the supermassive black hole at the center of the galaxy M87, about 55 million light-years away. The iconic image of a dark center surrounded by a glowing ring of hot, accreting gas confirmed decades of theoretical predictions and provided a rare visual insight into these otherwise invisible giants. Time dilation, a strange phenomenon predicted by Einstein's theory of general relativity, occurs near black holes and further adds to their mystique. As objects approach a black hole, time slows down relative to an observer at a safe distance. If a spaceship were to venture close to a black hole, its crew might experience only minutes while years could pass for observers far away. This concept, often illustrated in science fiction, raises fascinating questions about the nature of time itself and our potential for future interstellar travel. The role of black holes in shaping galaxies and even influencing the formation of stars and planets is another field of ongoing research. Although black holes are typically known for their destructive capabilities, they also play a surprisingly constructive role in the cosmos. The intense gravitational forces exerted by black holes can trigger bursts of star formation and influence the distribution of matter across galaxies. Supermassive black holes at the centers of galaxies often have accretion disks, swirling, superheated regions of gas and dust that emit vast amounts of energy, impacting everything in their vicinity. This energy output, sometimes called feedback, is thought to regulate the growth of galaxies, acting almost like a cosmic thermostat. One of the most thrilling hypotheses in black hole research today is the existence of primordial black holes, which may have formed shortly after the Big Bang. Unlike their massive, star-born counterparts, these black holes would be incredibly small, perhaps no larger than an atom. Yet, due to their intense density, they could still contain as much mass as a mountain. Scientists speculate that primordial black holes could account for some, or even all of the elusive dark matter in the universe. If proven, this would provide a revolutionary insight into one of the biggest mysteries in cosmology. Some theories also suggest that the universe we live in may have been born from a black hole in a higher dimensional space. This controversial idea, sometimes referred to as the black hole genesis theory, posits that what we perceive as the Big Bang could have been the formation of a black hole in another universe. Though speculative, such ideas push the boundaries of what we consider possible and force us to rethink our place within the multiverse. Gravitational waves, ripples in space-time caused by massive objects colliding, have also revealed new details about black holes. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first-ever gravitational waves produced by the merger of two black holes. These waves provided direct evidence of black hole collisions and opened an entirely new way to observe the universe. Since then, numerous gravitational wave detections have given scientists unprecedented insight into the lives of black holes, from their spins and masses to the cosmic environments in which they reside. As we peer further into space with advanced telescopes and analyze data with increasingly sophisticated models, our understanding of black holes continues to evolve. While many questions remain unanswered, each discovery brings us closer to unraveling the mysteries of these enigmatic objects. Black holes challenge us to think beyond the limits of human experience, to question the nature of reality itself, and to embrace the possibility that the universe is far more strange and wondrous than we ever imagined. The study of black holes is not just a journey into the unknown. It is a voyage into the very heart of what it means to explore, to seek knowledge, and to expand the horizons of human understanding. In a universe that is constantly revealing its secrets, black holes stand as profound reminders of both the limits and the boundless potential of science. As we dive deeper into the mysteries of black holes, we find ourselves asking not only what they are, but also how they might change our understanding of existence itself. One of the more startling ideas emerging from black hole research is the concept of holographic principles. This theory suggests that everything we perceive as three-dimensional might actually be encoded on a two-dimensional surface, much like a hologram. Black holes, with their powerful gravitational pull and event horizons, might hold clues to understanding if our reality is in fact a projection. This concept, though still in theoretical stages, challenges our perception of space, matter, and even consciousness. The event horizon of a black hole, often called the point of no return, represents the boundary beyond which nothing, not even light, can escape. It is here that the force of gravity is overwhelming, and any object crossing this line is inevitably pulled toward the singularity. What happens to matter as it crosses this boundary? Some theories propose that it gets spaghettified, stretching out due to the intense gravitational forces before being consumed. However, other theories suggest that the matter might instead be frozen in time, perpetually caught at the edge of the event horizon from an outside perspective. This idea plays with our understanding of time and motion, raising questions about whether matter is ever truly lost in a black hole or if it lingers in some strange state between existence and non-existence. A particularly intriguing concept related to black holes is white holes. White holes are theoretical opposites of black holes. Instead of pulling matter in, they would expel it. While no white holes have been observed, some scientists speculate that they might be connected to black holes, potentially even forming wormholes or passages between distant parts of the universe. If this theory holds, it could mean that black holes aren't the end of a journey through space-time, but rather gateways to unexplored regions of the cosmos. Imagine traveling through a black hole and emerging in an entirely different galaxy, or perhaps even a different universe. Such ideas are speculative, but incredibly enticing for the future of interstellar exploration. The concept of black hole jets offers another fascinating phenomenon. When matter spirals into a black hole, some of it gets compressed and heated to extraordinary temperatures, emitting powerful jets of energy that can travel vast distances across space. These jets, often seen from supermassive black holes, play a crucial role in the cosmos. They can influence star formation, impact galactic evolution, and even create massive cosmic structures known as radiolobes. Observing these jets allows scientists to study black holes indirectly and to understand their impact on their surrounding environments, turning what appears as a destructive force into one that profoundly shapes the universe. Quantum mechanics and general relativity, two of the most foundational theories in physics, offer conflicting descriptions of black holes, leading to ongoing debates and research. General relativity describes black holes as smooth, predictable objects governed by gravity and the geometry of space-time. Quantum mechanics, however, paints a different picture, one in which particles and energy are unpredictable and can exist in multiple states simultaneously. These two theories currently clash at the singularity of a black hole, where gravity is infinitely strong and quantum effects dominate. This incompatibility suggests that our understanding of black holes may require a new, unified theory of quantum gravity, an elusive concept that could bridge the gap between these two pillars of physics. One of the most mind-bending hypotheses surrounding black holes is that of firewalls. In 2012, a group of physicists proposed that there could be a wall of high-energy particles surrounding the event horizon, effectively burning anything that crosses it. This idea arose as a potential solution to the information paradox, as it suggests that information about objects falling into a black hole might be encoded in this firewall. However, the concept of firewalls remains highly controversial, as it conflicts with other established principles in physics, such as the smoothness of space-time at the event horizon. If proven, firewalls would radically alter our understanding of what black holes are and how they interact with the universe around them. Even more enigmatic is the idea that black holes might leak into other dimensions. In some models of the universe, especially those involving string theory, there could be extra spatial dimensions beyond the familiar three. Black holes, with their immense gravitational pull, might have the ability to poke into these dimensions, drawing matter and energy into realms we cannot perceive. If this is true, then black holes could be bridges not only across space and time, but across dimensions, hinting at a multiverse where each black hole could lead to a new universe entirely. While these ideas are far from confirmed, they offer a thrilling possibility that black holes might be more than cosmic endpoints. They could be connections to new forms of existence. In recent studies, some physicists have suggested that black holes might not even exist in the way we think. According to these models, what we perceive as a black hole might instead be a dense cluster of dark energy or exotic particles. This interpretation challenges the very concept of the singularity and the event horizon, proposing instead that matter might simply be compressed into an ultra-dense state without the traditional point of no return. If true, this would mean that black holes are not cosmic traps, but rather incredibly dense regions where strange forms of matter and energy coexist. Hawking radiation, a theoretical prediction by Stephen Hawking, suggests that black holes might slowly evaporate over time. This phenomenon arises from quantum effects near the event horizon, where particle-antiparticle pairs spontaneously appear and vanish. When one particle is captured by the black hole and the other escapes, it creates the effect of radiation, allowing the black hole to lose mass over extremely long timescales. This slow evaporation process raises intriguing questions about the ultimate fate of black holes. Could they eventually vanish, leaving behind only a faint imprint on space-time? Or might their remnants offer some insight into the structure of the universe itself? Some scientists speculate that black holes might contain baby universes. According to this hypothesis, the singularity at the core of a black hole could create a new universe within it, possibly with different physical laws. From our perspective, this baby universe would remain hidden, separated by the event horizon, but from within, it might appear like an entire cosmos. This idea aligns with some theories about the multiverse, where each black hole could spawn a new universe with its own distinct characteristics. If this theory holds, black holes might be creators rather than destroyers, sowing the seeds of new worlds across the multiverse. The future of black hole research holds even greater potential, especially as we develop new observational tools. The upcoming James Webb Space Telescope and the next generation Event Horizon Telescope will allow us to observe black holes with greater clarity and precision. These tools may help answer long-standing questions, like the nature of black hole mergers, the existence of intermediate black holes, and the dynamics of matter in the intense gravitational fields surrounding black holes. Each technological advancement brings us closer to unlocking the secrets of these cosmic enigmas and understanding how they fit into the broader narrative of the universe. As our understanding of black holes deepens, so too does our curiosity. These objects defy easy explanations, lying at the crossroads of reality and mystery. They offer a glimpse into the most extreme conditions imaginable, where gravity reigns supreme and where the boundaries between time, space, and matter blur into one. To study black holes is to push the limits of human knowledge, to stand at the edge of what we know and peer into the unknown, embracing the possibility that the universe is infinitely more complex, beautiful, and mysterious than we ever dreamed. Black holes, in their dark silence, challenge us to question the nature of existence, to redefine our understanding of space and time, and to acknowledge the profound mysteries that still lie beyond our reach. They remind us that the cosmos is filled with wonders yet to be discovered, inviting us on a journey that transcends the boundaries of science and touches the very core of human imagination. As we continue to unravel the mysteries of black holes, we step closer to answering some of the most profound questions of our existence, venturing into the unknown with curiosity and wonder as our guiding stars. As we continue our journey through the incredible mysteries of black holes, we encounter yet another fascinating concept: black holes as potential time machines. According to the theory of general relativity, black holes distort space-time to such a degree that they could theoretically allow for time travel. Near the event horizon, time slows down dramatically relative to an observer at a safe distance, a phenomenon known as time dilation. In extreme cases, if a spaceship were to venture near a black hole and return, its crew might experience only a few hours while centuries pass in the outside universe. This time-warping effect has been a favorite theme in science fiction, but it's grounded in real physics. The idea that black holes could enable one-way travel to the future invites us to reconsider our conventional understanding of time as a straight line. The possibility of time loops near black holes leads us into even more intriguing realms. Some physicists propose that black holes might contain closed time-like curves, paths in space-time that loop back on themselves. In theory, these curves could allow an object to return to its own past. However, the concept raises significant paradoxes, like the classic grandfather paradox, where altering the past could prevent one's own existence. While these ideas remain speculative, they push the boundaries of what we think we know about causality, time, and the fundamental structure of reality. Our exploration of black holes also brings us face to face with the strange phenomenon of quantum entanglement. This is a situation where particles become interconnected, such that the state of one particle instantly influences the state of another, regardless of the distance between them. Physicists speculate that black holes might play a role in entangling particles across vast stretches of space, potentially linking distant regions of the universe in ways we don't yet understand. This spooky action at a distance, as Einstein called it, could mean that black holes are more than cosmic sinkholes. They could be active participants in a universe where everything is interconnected at a quantum level. Then there's the intriguing concept of soft hair, a theory proposed to solve the black hole information paradox. Traditional models suggest that information about objects falling into a black hole is irretrievably lost, which contradicts the principles of quantum mechanics. But the soft hair hypothesis proposes that black holes might retain traces of this information on their surfaces. These tiny imprints, or hairs, could encode information about everything that has ever fallen into the black hole, like a cosmic ledger. If true, this could mean that black holes don't destroy information entirely. Instead, they might preserve it in a form we have yet to decipher. Another captivating area of black hole research involves black hole thermodynamics, a field that treats black holes as objects with temperature, entropy, and even a kind of pressure. Stephen Hawking's work showed that black holes emit radiation, meaning they have a temperature and can slowly lose mass over time. This discovery was groundbreaking, as it linked black holes to the principles of thermodynamics and quantum mechanics. The study of black hole entropy, in particular, suggests that black holes might be a window into understanding the very nature of entropy and the arrow of time. It even leads to the idea that the universe itself, as a closed system, might have properties similar to a massive, all-encompassing black hole. The question of naked singularities also intrigues scientists and theorists alike. In most cases, black holes have an event horizon that conceals the singularity within. However, some solutions to Einstein's equations predict the possibility of singularities without an event horizon, known as naked singularities. These would be regions where the laws of physics as we know them completely break down and are visible to the outside universe. If naked singularities exist, they could potentially reveal unprecedented information about the fabric of space-time and the nature of gravity. Observing a naked singularity could be like peering into the raw code of the universe, unlocking secrets that have remained hidden behind the event horizons of traditional black holes. The concept of fuzzballs, a theory arising from string theory, offers yet another fascinating interpretation of black holes. According to string theory, instead of having a singularity at their core, black holes might be composed of tangled strings, forming a dense fuzzball. This model eliminates the singularity and suggests that black holes could have a finite structure made up of strings vibrating at different frequencies. This theory not only provides a possible solution to the information paradox, but also introduces the idea that black holes might be more like complex, structured objects rather than points of infinite density. The fuzzball theory is still in its early stages, but it offers a tantalizing glimpse into how black holes might look through the lens of string theory. Our understanding of black holes has also been revolutionized by the recent detection of intermediate mass black holes. For decades, scientists were aware of stellar black holes and supermassive black holes, but struggled to confirm the existence of black holes of medium size. These intermediate mass black holes could help bridge the gap between the small and large ends of the black hole spectrum, shedding light on how black holes grow and evolve. Studying these middleweight black holes could also reveal how supermassive black holes form at the centers of galaxies, an essential puzzle in understanding the architecture of the cosmos. One of the most fascinating aspects of black hole research is how it intersects with the field of dark matter. Some theories suggest that black holes, especially primordial black holes, could make up a portion of the universe's dark matter, an invisible substance that constitutes around 85% of all matter in the cosmos. If black holes indeed contribute to dark matter, it could mean that these enigmatic objects are far more abundant than we realize, scattered across the universe in ways that are detectable only by their gravitational effects. This hypothesis has inspired countless studies, as confirming a connection between black holes and dark matter would revolutionize our understanding of both phenomena. Looking at the future of black hole exploration, scientists are now developing ways to simulate black hole conditions in laboratories on Earth. Using high-powered lasers and particle accelerators, researchers can create miniature analogs of black holes, allowing them to observe phenomena like Hawking radiation under controlled conditions. While these experiments cannot replicate the full complexity of actual black holes, they offer valuable insights into the behavior of matter and energy under extreme gravitational forces. Laboratory analogs of black holes also provide a testbed for theories about gravity, quantum mechanics, and even potential ways to unify these two fields. The mysteries of black holes invite us to imagine what lies beyond the observable universe. Could black holes be cosmic archives, storing information about everything that has ever fallen into them? Are they tunnels to other universes, connected by unseen threads of space-time? Or might they be the ultimate laboratories of creation, seeding new realms of existence with each collapse? Every answer we uncover about black holes seems to open the door to new, even more profound questions, reminding us that the universe is filled with secrets that we have only begun to explore. Ultimately, Black holes are far more than objects of destruction. They are engines of creation, information, and possibility. They embody the paradoxes and mysteries at the heart of the cosmos, challenging us to rethink the very nature of existence and pushing us to explore realms of knowledge that once seemed beyond reach. In a universe defined by discovery and wonder, black holes remain one of the greatest enigmas, calling us ever onward into the vast unknown, where every answer leads to new mysteries and every mystery to new frontiers. As we continue our exploration into the depths of black hole mysteries, we encounter the tantalizing question of whether black holes might somehow talk to one another. Though it may sound like science fiction, recent theories propose that black holes might interact through subtle quantum connections known as wormholes or Einstein-Rosen bridges. According to this idea, two black holes separated by vast distances could be quantum entangled, sharing information instantaneously across the cosmos. If true, this phenomenon would mean that black holes are not isolated cosmic entities, but are instead part of a hidden network, transferring information in ways we can barely comprehend. This concept aligns with the holographic principle, suggesting that the universe is interconnected on a fundamental level, with black holes playing a crucial role in this cosmic web. The mystery deepens when we consider the implications of black holes for the birth of our universe itself. Some scientists have proposed a radical hypothesis. Our entire universe might have emerged from a black hole in another parent universe. This black hole cosmology suggests that every black hole could be the seed of a new universe, forming a kind of cosmic tree with each branch leading to a different reality. If true, this would mean that our universe is but one of countless others, each with its own set of physical laws and constants, each evolving in parallel or sequentially across a vast multiverse. The idea that our universe might exist within the event horizon of a colossal black hole in another realm adds a mind-bending twist to our understanding of existence and origins. Exploring the boundaries of black hole theory brings us to the concept of Planck stars. According to some quantum gravity models, black holes might not end in singularities after all. Instead, they could collapse to a very dense but finite object known as a Planck star, named after the smallest measurable length in physics, the Planck length. In this model, black holes would undergo a bounce effect, where, after collapsing to a Planck star, they might eventually release their energy back into space. This process, though likely to take far longer than the current age of the universe, suggests that black holes could eventually explode, releasing all the matter they've absorbed in a massive burst of energy. If this theory holds, black holes would not be eternal tombs, but temporary cosmic vaults, eventually releasing what they had taken, leaving us with a new understanding of cycles in the universe. One of the most intriguing debates in black hole physics today centers on the nature of gravity and its relationship with quantum mechanics. Black holes exist at the intersection of general relativity, which describes gravity on large scales, and quantum mechanics, which governs the behavior of particles at the smallest scales. The clash between these two theories becomes evident at a black hole's singularity, where gravity is infinitely strong and quantum effects are at their peak. Scientists hope that studying black holes will eventually lead to a theory of everything, a unified framework that can explain both gravity and quantum mechanics. Such a theory would not only answer questions about black holes, but also transform our understanding of the fundamental forces that govern the universe. This quest for a unified theory has led to the study of loop quantum gravity, an alternative approach to understanding black holes. Unlike traditional theories, which view space-time as a smooth, continuous fabric, loop quantum gravity proposes that space-time is made up of discrete, tiny loops. In this view, black holes might not be smooth entities with a singularity at their core, but instead complex networks of loops that eliminate the need for a singularity. This theory also suggests that black holes could have quantum surfaces, where information about the universe is encoded in the form of quantum loops. If true, loop quantum gravity could revolutionize our understanding of black holes, offering a model that combines the principles of quantum mechanics and general relativity without the need for a singularity. Another captivating aspect of black holes is their influence on the universe's structure. Though often thought of as cosmic destroyers, black holes play a vital role in the formation and stability of galaxies. At the center of nearly every large galaxy lies a supermassive black hole, whose gravitational pull helps hold the galaxy together. These central black holes regulate the flow of gas and stars within galaxies, shaping their evolution over billions of years. In fact, it's possible that galaxies themselves could not form without these powerful anchors at their cores. The interplay between black holes and galaxies reveals that black holes are not merely cosmic predators, but essential architects of the universe's grand design. In the early universe, black holes may have acted as cosmic seeds, catalyzing the formation of large-scale structures. Some theories suggest that primordial black holes, formed shortly after the Big Bang, could have provided the gravitational seeds necessary for galaxies to coalesce. As these primordial black holes attracted gas and dust, they may have created the first clusters of stars and, eventually, galaxies. If primordial black holes exist, they could provide clues about the earliest moments of the universe, including insights into dark matter and the mysterious forces that shape the cosmos we see today. One of the more outlandish but fascinating ideas surrounding black holes is the concept of black hole-powered civilizations, known as Kardashev Type 3 civilizations in theoretical astrophysics. These are advanced societies that might harness the energy output of black holes to power their entire civilization. By tapping into the immense energy released by the accretion disks and jets around supermassive black holes, these hypothetical civilizations could achieve unprecedented technological feats. The possibility of black hole-powered civilizations raises questions about whether other forms of life might exist in ways we cannot yet imagine, using the universe's most extreme environments as sources of energy and innovation. Black holes also inspire us to rethink the concept of boundaries in the universe. With the discovery of the first real image of a black hole's event horizon, scientists have been able to observe the edge of these enigmatic objects. This shadow of a black hole, the dark region where light can no longer escape, offers a rare look at where space-time itself becomes distorted. Studying this boundary allows physicists to probe the limits of physical laws, gaining insights into how extreme gravity distorts light, time, and space. The shadow of a black hole acts as a window into the unknown, showing us the limits of what we can observe and challenging us to expand our knowledge beyond the visible universe. Our fascination with black holes reflects a deeper desire to understand the unknown and to explore the frontiers of existence. These mysterious objects embody some of the most profound questions in science, touching on the nature of reality, the fabric of space and time, and even the meaning of life itself. As we continue to study black holes, we are not merely observing distant cosmic phenomena. We are exploring the fundamental forces that govern all of existence, pushing the limits of human knowledge and imagination. Black holes are far more than just strange objects lurking in space. They are portals to new realms of knowledge, both scientific and philosophical. They remind us that the universe is a place of boundless possibilities, where each discovery leads to new questions, and where every answer opens doors to deeper mysteries. As we stand on the brink of uncovering more about these enigmatic giants, black holes invite us to dream, to imagine, and to explore a cosmos filled with wonders we have only begun to understand. As we delve further into the captivating mysteries of black holes, we arrive at one of the most mind-bending concepts: the potential of black holes to create new universes. This idea, known as cosmological natural selection or the Fekin universes hypothesis, suggests that black holes might give birth to new universes with physical constants slightly different from their parent universe. In this theory, each universe produces black holes, which, in turn, generate new universes in a never-ending cycle of cosmic reproduction. Each offspring universe could have slight variations in the laws of physics, leading to a kind of survival of the fittest scenario where universes that produce more black holes are more likely to propagate. This radical theory, though highly speculative, offers an astonishing new perspective on why our universe might be finely tuned for the existence of stars, galaxies, and even life itself. Another fascinating aspect of black hole research is the recent exploration of exotic matter in theoretical physics. For a long time, black holes were believed to trap everything within their event horizon, rendering anything inside forever lost to the outside universe. However, The study of exotic matter, matter with negative energy or negative mass, has led to new possibilities. If exotic matter exists, it might allow for stable wormholes or tunnels between black holes, effectively creating a shortcut through space and time. These wormholes, if they could exist, would not only challenge our understanding of black holes, but could also open the door to interstellar or even intergalactic travel. The presence of exotic matter would alter the structure of space-time, allowing particles, or even spacecraft, to traverse black holes and emerge elsewhere, perhaps in another part of the universe, or even another universe altogether. One of the most controversial theories surrounding black holes is the concept of firewalls, an idea that contradicts the traditional view of the event horizon as a smooth boundary. In this theory, an object crossing the event horizon would encounter a wall of intense radiation, disintegrating upon contact. This concept, initially proposed to solve the information paradox, suggests that rather than smoothly crossing into the black hole, objects would meet an abrupt end, with their information encoded on this energetic barrier. While firewalls remain unproven, they represent a bold attempt to reconcile quantum mechanics with the behavior of black holes. If proven, firewalls would redefine our understanding of black hole boundaries, challenging the assumption that information disappears or is conserved in a black hole. Black holes have also provided a new perspective on the nature of information itself. According to the principles of quantum mechanics, information about physical systems cannot be destroyed. However, black holes appear to violate this rule, as anything that enters a black hole seems to vanish without a trace. This problem, known as the black hole information paradox, has led scientists to explore whether black holes might actually store information in a highly encrypted, holographic form. This idea, rooted in the holographic principle, suggests that information falling into a black hole could be preserved on its surface, encoded in quantum bits or qubits. If correct, this theory implies that black holes are not merely destructive forces but cosmic vaults, holding encrypted records of everything that has ever fallen into them. In the realm of astrophysics, black holes are now understood to play a crucial role in the life cycle of galaxies. Far from being isolated anomalies, black holes appear to regulate the formation and evolution of entire galaxies. The energy output from supermassive black holes, especially those actively consuming matter, can create powerful jets and winds that heat surrounding gas, preventing it from collapsing into new stars. This feedback mechanism helps control the pace of star formation and shapes the structure of galaxies. By moderating the amount of gas available for star formation, black holes essentially act as cosmic gardeners, cultivating galaxies and shaping the environments that may eventually support planets and life. The relationship between black holes and dark matter is another fascinating area of study. Dark matter, an invisible substance that makes up most of the universe's mass, interacts with regular matter only through gravity. Some scientists hypothesize that black holes might attract dark matter, forming halos or dense regions of dark matter around them. This connection could potentially help scientists understand the nature of dark matter and its distribution throughout the universe. If black holes indeed gather dark matter, they could serve as gravitational lenses, magnifying light from distant objects and allowing astronomers to indirectly observe the influence of dark matter. By studying the way light bends around black holes, researchers hope to uncover clues about this mysterious substance that plays a critical role in the cosmos. Another thrilling possibility is that black holes might be capable of creating echoes in space-time. Recent gravitational wave observations have suggested that, after two black holes merge, they might produce faint echoes as the fabric of space-time settles. These echoes could provide insight into the true nature of black holes, including whether they have the smooth event horizons described by general relativity or whether they possess a more complex structure. Detecting and studying these echoes could reveal unprecedented details about the dynamics of black hole mergers and the properties of space-time itself. The advent of gravitational wave astronomy has opened up a new era of black hole discovery. Gravitational waves, ripples in space-time caused by massive objects colliding, provide a direct way to observe black hole mergers and detect black holes that were previously invisible. Since the first detection in 2015, gravitational wave observatories like LIGO and Virgo have recorded numerous black hole mergers, allowing scientists to measure their masses, spins, and even the environments in which they reside. This data has not only confirmed the existence of intermediate mass black holes, but has also provided evidence of hierarchical mergers, where black holes that formed from previous mergers collide again, creating even larger black holes. Gravitational wave astronomy has turned the universe into a cosmic symphony, allowing us to listen in on the colossal collisions that shape the cosmos. As we look to the future, the study of black holes promises to uncover even more remarkable insights. The development of next-generation observatories, including space-based gravitational wave detectors like LISA, Laser Interferometer Space Antenna, will allow scientists to detect black hole mergers across the universe, from small stellar mass black holes to the most massive supermassive black holes. These advanced instruments will enable us to observe black hole mergers in distant galaxies, explore the formation of black holes in the early universe, and perhaps even catch glimpses of primordial black holes if they exist. Black holes continue to push the boundaries of science and imagination, challenging us to consider realms of existence that defy conventional understanding. They are windows into the extreme, where gravity reigns supreme and where the known laws of physics break down. Each discovery and theory about black holes brings us closer to understanding the fundamental principles that govern the universe, from the smallest quantum particles to the largest cosmic structures. In their silent darkness, black holes hold the answers to some of the universe's deepest questions about time, space, and the very nature of reality. They compel us to venture into the unknown, to embrace the mysteries that lie beyond our reach, and to recognize that the universe is an endless well of secrets waiting to be uncovered. As we probe the depths of black holes, we are not merely studying distant objects in space. We are exploring the boundaries of human knowledge, unlocking new ways of understanding existence, and opening doors to a future filled with discoveries as vast and mysterious as the cosmos itself. As we journey further into the enigmatic realms of black holes, we encounter one of the most speculative yet tantalizing ideas: the possibility of black holes as pathways to alternate universes. According to certain interpretations of quantum mechanics and general relativity, a black hole might not simply be an endpoint where matter is lost forever. Instead, it could act as a bridge, a wormhole, leading to a completely different universe. In this theory, when matter is pulled into a black hole's singularity, it may emerge in another region of space-time, or even in a parallel universe, effectively making black holes a cosmic transit system across multiple dimensions. This idea, though largely theoretical, raises questions about whether black holes might serve as portals, and if so, what these alternative realities might look like. The concept of parallel universes, or a multiverse connected by black holes, opens a doorway to profound questions about existence and the nature of reality. If black holes are indeed connected to other universes, each could possess its own physical laws, constants, and forms of life entirely alien to our understanding. This idea aligns with certain interpretations of the many worlds hypothesis in quantum mechanics, which proposes that every possible outcome of every event exists in its own parallel universe. If black holes act as gateways between these universes, then they might offer clues to the hidden dimensions of a multiverse beyond our observational reach. The possibility of using black holes for time travel is another concept that blurs the line between science and science fiction. Einstein's theory of general relativity suggests that black holes warp space-time to an extreme degree, and near their event horizons, time slows dramatically. If a spacecraft were able to orbit near a black hole without crossing the event horizon, it might experience time dilation so intense that only hours or days would pass for the crew while years, or even centuries pass in the outside universe. This effect, sometimes called gravitational time dilation, provides a one-way form of time travel to the future. However, the challenges of safely approaching a black hole without being consumed by it make this form of time travel a theoretical fascination rather than a practical reality, at least for now. An equally compelling notion is the idea that black holes might serve as cosmic record keepers. The hypothesis that black holes might preserve information about every particle and event that has ever entered them is rooted in the holographic principle. This principle suggests that all the information contained within a black hole could be encoded on its surface, much like a hologram stores a three-dimensional image on a two-dimensional surface. If this theory is correct, then black holes are not empty voids but complex archives, preserving the histories of galaxies, stars, and even life forms that they have consumed. This idea resonates with the notion that black holes might play a more constructive role in the universe, serving as cosmic libraries that encode and store the information about everything that has ever existed. Our understanding of black holes has also led to the intriguing theory of black hole computers or quantum computers. Some physicists propose that black holes could, in theory, function as natural quantum computers, processing and storing vast amounts of information on a scale unimaginable by human technology. In this view, black holes are not merely passive objects but active processors of information, utilizing the laws of quantum mechanics to encode data on their surfaces. This concept could be foundational in the search for quantum gravity, as it suggests that black holes operate at the intersection of relativity and quantum mechanics, offering a natural laboratory for studying how these forces interact. The idea of a black hole as a quantum computer hints at the potential for black holes to provide a blueprint for advanced computation, possibly serving as a model for creating powerful, artificial quantum systems. The search for microscopic or primordial black holes is another area of fascination in astrophysics. These black holes, thought to have formed in the earliest moments after the Big Bang, could be incredibly small, perhaps no larger than an atom, but with masses comparable to a mountain. If primordial black holes exist, they could account for a portion of the universe's dark matter, the mysterious substance that comprises most of the matter in the cosmos but cannot be observed directly. Detecting these tiny black holes would not only confirm their existence, but also offer insights into the structure of the early universe and the nature of dark matter, helping to answer fundamental questions about the building blocks of everything we know. The role of black holes in cosmic evolution is another intriguing aspect that challenges our conventional understanding of how galaxies form and evolve. Black holes, particularly supermassive ones, act as cosmic regulators, influencing the pace of star formation in galaxies through a process known as feedback. As gas and dust spiral into a black hole, the intense energy released by this activity generates powerful winds and jets that push surrounding material outward. This feedback mechanism can halt star formation by heating the gas around the black hole, preventing it from cooling and collapsing into new stars. Thus, black holes play an unexpected role in pruning galaxies, regulating their growth and structure over billions of years, and ensuring that galaxies evolve in complex yet balanced ways. The discovery of gravitational waves has transformed our ability to study black holes. When black holes merge, they release gravitational waves, ripples in the fabric of space-time, that can be detected by observatories on Earth. These waves carry information about the masses, spins, and distances of the merging black holes, allowing scientists to study black hole mergers with unprecedented detail. Since 2015, when the first gravitational waves were detected, observatories like LIGO and Virgo have captured numerous black hole mergers, revealing that these cosmic collisions are more common than previously thought. Gravitational wave astronomy has opened a new window into the cosmos, enabling us to observe events that were once invisible and offering a fresh perspective on how black holes interact and evolve. Some scientists are now exploring the possibility that black holes might influence the expansion of the universe itself. According to the latest research, the mysterious dark energy driving the accelerated expansion of the universe might be related to the properties of black holes. Dark energy, which makes up about 70% of the universe's energy density, is currently one of the greatest enigmas in cosmology. Some theories propose that black holes could serve as reservoirs for dark energy, with their gravitational properties contributing to the universe's expansion. If this connection is proven, it would fundamentally reshape our understanding of both black holes and the overall structure of the universe, offering a potential link between the smallest and largest scales in the cosmos. The future of black hole research is full of promise, as new technologies and observational techniques continue to emerge. Next-generation telescopes, both ground-based and space-based, will enable astronomers to observe black holes with higher resolution and sensitivity than ever before. Instruments like the James Webb Space Telescope will allow scientists to peer into the cores of distant galaxies and study supermassive black holes at cosmic dawn, helping us understand how these giants formed and evolved. Additionally, proposed space-based gravitational wave observatories, like the Laser Interferometer Space Antenna, LISA, will allow us to detect gravitational waves from black hole mergers across the universe, expanding our reach and enabling us to observe black hole collisions from the distant past. Black holes challenge us to rethink our understanding of the universe on every level. They raise questions about the nature of time, the structure of space-time, and even the concept of reality itself. Through the study of black holes, we are not merely uncovering details about exotic celestial objects. We are exploring the limits of human knowledge and venturing into realms that have long been shrouded in mystery. As we continue to probe these cosmic giants, we are reminded of the vastness and complexity of the universe, and of our own small but significant role within it. Black holes are far more than just cosmic enigmas. They are profound symbols of the unknown, embodying the mysteries that lie beyond the horizon of human understanding. They inspire us to reach deeper into the cosmos, to ask bigger questions, and to embrace the unknown with curiosity and wonder. Each new discovery about black holes brings us closer to a universe that is stranger and more wondrous than we could have ever imagined, inviting us to continue our exploration of the infinite mysteries that await us in the vast, silent darkness of space. As we continue unraveling the mysteries surrounding black holes, we arrive at one of the most profound questions in physics. Could black holes offer us clues to a theory of everything? A theory of everything would unify all fundamental forces of nature into a single framework, bridging the gap between general relativity, which describes gravity on cosmic scales, and quantum mechanics, which governs the behavior of particles on the smallest scales. Black holes are uniquely suited to this challenge because they exist at the intersection of these two realms, with gravity so strong that quantum effects become significant. Many scientists believe that understanding black holes could be the key to developing a quantum theory of gravity, potentially reshaping the foundations of physics and revealing a deeper structure to reality. One approach to this quest involves the idea of string theory, which posits that all particles are made of tiny, vibrating strings. According to string theory, black holes could be composed of these strings as well, with the singularity, the point of infinite density at their core, replaced by a complex, tangled network of strings. This perspective introduces the idea of fuzzballs, where black holes have a definite, finite structure made of strings, eliminating the need for a singularity. If black holes are indeed fuzzballs, this would resolve many theoretical paradoxes and provide a path toward unifying gravity with quantum mechanics. This approach could make black holes a testing ground for string theory, offering insights that might reveal the true nature of the universe at its most fundamental level. In recent years, scientists have also explored the concept of quantum foam, a chaotic and unpredictable structure that might exist at the smallest scales of space-time. At the quantum level, space-time is thought to be foamy, with particles constantly popping in and out of existence. Black holes, with their extreme gravitational fields, may provide a glimpse into this quantum foam, allowing scientists to study how space-time behaves under the most intense conditions imaginable. If quantum foam exists, it could mean that black holes are not smooth entities but instead fluctuate at microscopic levels, shaped by the constant dance of quantum particles. This understanding could lead to breakthroughs in our comprehension of space-time, potentially merging quantum mechanics and general relativity in a way that fundamentally alters our understanding of reality. The concept of holographic duality is another revolutionary idea that black holes have inspired. According to this theory, everything inside a black hole could be described by information encoded on its two-dimensional surface, much like a hologram. This principle could extend beyond black holes, suggesting that the entire universe might function as a hologram, where the three-dimensional reality we perceive is merely a projection of information on a two-dimensional surface. If this holographic principle holds true, it would transform our understanding of space and time, implying that reality itself is more digital and less solid than we think. Black holes could thus reveal that our universe is fundamentally a vast, interconnected web of information, reshaping our perception of existence itself. As we peer deeper into the mysteries of black holes, we also encounter theories involving their role in the origin of the universe. One hypothesis proposes that our universe could have been born from a black hole in a higher dimensional space, a process known as black hole cosmology. In this scenario, the Big Bang might represent the formation of a black hole in another realm, with our universe emerging from the event horizon as a new, self-contained cosmos. This concept not only offers a potential explanation for the origin of our universe, but also suggests that every black hole in our universe could be the seed of a new universe within it. If true, black holes are not merely points of destruction. They are cosmic wombs, giving birth to new realities, each with its own unique set of physical laws and possibilities. The quest to understand black holes has also driven research into information theory, a field that examines how information is processed, stored, and transmitted. Black holes challenge the fundamental principles of information theory, as they seem to erase information about the objects that fall into them, creating the infamous information paradox. However, recent research suggests that black holes might preserve information on their event horizons in scrambled form, a concept rooted in quantum mechanics. This realization could reshape our understanding of information itself, showing that information is never truly lost, but simply transformed in ways we have yet to fully grasp. By studying black holes, we are not only exploring cosmic objects, but also testing the limits of how information interacts with matter, energy, and space-time. The nature of black hole entropy is another profound mystery that continues to challenge scientists. Entropy, a measure of disorder, plays a key role in the study of thermodynamics, and black holes exhibit unique thermodynamic properties. Stephen Hawking's work demonstrated that black holes emit radiation, known as Hawking radiation, and have a temperature, meaning they can slowly lose mass and evaporate over time. This radiation implies that black holes have entropy, which is proportional to the surface area of their event horizon rather than their volume. This relationship between a black hole's surface area and its entropy suggests a deep connection between black holes and the fundamental nature of thermodynamics, possibly hinting at a new understanding of the laws governing entropy and the arrow of time in the universe. In the realm of quantum mechanics, black holes have also led to theories about quantum entanglement. Entanglement is a phenomenon where two particles become linked, so the state of one particle instantaneously influences the state of the other, even if they are separated by vast distances. Some scientists believe that black holes could serve as hubs of entanglement, connecting particles across the universe in ways we don't yet fully understand. This concept suggests that black holes are not isolated entities, but could play a role in a vast network of connections that span the cosmos, linking particles, stars, and galaxies through quantum states. If this is true, black holes might act as cosmic routers in an invisible web that binds the universe together at a fundamental level, revealing that everything is more interconnected than we ever imagined. Another exciting frontier in black hole research is the study of dark energy and dark matter, two mysterious forces that shape the universe yet remain invisible to us. Dark matter, which makes up most of the universe's mass, does not emit light or interact with regular matter except through gravity. Some scientists speculate that black holes, especially primordial ones formed shortly after the Big Bang, could account for a portion of dark matter. Similarly, dark energy, which drives the accelerated expansion of the universe, might be influenced by black holes' gravitational properties. If black holes contribute to these elusive forces, they could provide a crucial link in understanding the composition and ultimate fate of the universe, revealing how ordinary matter, and dark energy interact on cosmic scales. The future of black hole exploration promises to push the boundaries of science even further. Advanced telescopes, gravitational wave detectors, and particle accelerators will allow scientists to probe the details of black hole formation, growth, and mergers. Upcoming missions like the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory, will detect black hole mergers across greater distances, capturing signals from black hole collisions that occurred billions of years ago. Meanwhile, the James Webb Space Telescope will observe supermassive black holes at the centers of distant galaxies, allowing us to study how these titanic objects influence galaxy formation in the early universe. Each new discovery brings us closer to unraveling the secrets of black holes and their role in shaping the cosmos. As we venture further into the unknown, black holes continue to serve as cosmic beacons, illuminating the deepest mysteries of existence. They compel us to question the nature of reality, the limits of knowledge, and the interconnectedness of all things. With every advance in black hole research, we are reminded that the universe is not only vaster and more complex than we can imagine, but also more intricately beautiful, challenging us to expand our horizons and embrace the mysteries that lie beyond. Black holes stand as profound symbols of the unknown, reminding us that in the darkness of the universe, there is always more to discover. They inspire us to look beyond the surface, to peer into the depths, and to embrace the idea that our journey of understanding is far from over. Each discovery about black holes opens a new chapter in our quest for knowledge, fueling our desire to explore, to question, and to seek answers to the mysteries that define our place in the cosmos. In their silent, enigmatic presence, black holes invite us to keep exploring, knowing that the greatest secrets of the universe are still waiting to be revealed. As we journey further into the enigmatic world of black holes, we encounter the question of whether black holes could be more than mere cosmic mysteries. They might hold the keys to understanding the origins and ultimate destiny of our universe. Recent research suggests that black holes could influence the very fabric of space-time in ways that are far more complex than previously imagined. Some theories propose that black holes may act as cosmic sculptors, not only shaping galaxies, but potentially affecting the large-scale structure of the universe itself. These ideas push us to consider black holes as active participants in the grand design of the cosmos, rather than passive entities lurking in the depths of space. One particularly groundbreaking concept is the idea that black holes could harbor the seeds of dark energy, the mysterious force responsible for the accelerating expansion of the universe. Scientists have long been puzzled by dark energy, which appears to push galaxies apart with ever-increasing speed. New theories suggest that black holes, particularly those at the centers of galaxies, might contribute to, or even generate dark energy. If true, this would imply that black holes are not just remnants of dead stars, but engines of cosmic expansion, influencing the universe on scales far beyond what we previously thought possible. This connection could redefine our understanding of both black holes and the forces driving the evolution of the universe, offering a unified explanation for phenomena that have remained elusive for decades. Another exciting development in black hole research is the study of black hole echoes. When black holes merge, they produce gravitational waves, ripples in space-time that we can detect on Earth. However, some scientists hypothesize that these gravitational waves may contain echoes that reveal new information about black holes' interiors or surfaces. These echoes could provide clues about the fundamental nature of black holes, possibly even indicating whether they have a smooth event horizon or a more complex structure. If black hole echoes can be detected and analyzed, they may offer insights into the very fabric of space-time and reveal whether black holes are governed by unknown physical principles. The discovery of echoes could open a new chapter in our understanding, revealing details about black hole mergers and the properties of space-time itself. As technology advances, scientists are also exploring the potential of black hole analogs on Earth. In laboratory settings, researchers have begun creating conditions that mimic certain aspects of black holes, allowing them to study phenomena like Hawking radiation in controlled environments. These artificial black holes do not possess the full power of their cosmic counterparts, but can replicate some of the quantum effects associated with black hole behavior. By observing how particles interact in these setups, scientists hope to gain new insights into black hole thermodynamics, quantum mechanics, and possibly even quantum gravity. Laboratory analogs could help bridge the gap between theory and observation, offering a practical way to explore black hole mysteries on Earth. The study of black holes also brings us to the concept of superradiance, a process where rotating black holes can amplify waves and particles that interact with them. This amplification process could, in theory, generate detectable signals, revealing information about the rotation and other properties of black holes. If we could harness the process of superradiance, it might even allow for methods of extracting energy from rotating black holes, opening the door to a new form of energy generation. Although highly speculative, this concept fuels our imagination about the future potential of black holes, not only as objects of study, but also as possible sources of untapped cosmic energy. One of the most challenging mysteries in black hole physics is the study of entropy and the arrow of time. In conventional thermodynamics, entropy, a measure of disorder, always increases, giving time its one-way direction. However, black holes have a unique relationship with entropy. Their entropy is proportional to the surface area of their event horizon, rather than their volume. This relationship suggests a deep connection between black holes, thermodynamics, and the passage of time. Some scientists believe that understanding black hole entropy could lead to breakthroughs in our understanding of time itself, possibly revealing why time flows in one direction and how this flow might relate to the universe's overall structure and eventual fate. Another fascinating area of black hole research is the possibility of black hole stars or quasi-stars. These hypothetical objects are thought to have existed in the early universe, forming when massive clouds of gas collapsed to form black holes surrounded by dense layers of gas. Black hole stars would be incredibly luminous, possibly thousands of times brighter than ordinary stars, due to the intense radiation emitted as gas falls into the central black hole. Studying these theoretical objects could provide insights into how the first supermassive black holes formed and how their intense radiation may have shaped the evolution of galaxies. If we could detect evidence of ancient black hole stars, it would offer a glimpse into the universe's earliest epochs, shedding light on how the cosmic landscape developed over billions of years. Recent advances in black hole research have also sparked new interest in the concept of Planck stars, a type of ultradense object that could exist within black holes. According to this theory, black holes might not end in singularities of infinite density, but rather in Planck stars, tiny, incredibly dense objects that prevent complete gravitational collapse. If Planck stars exist, they could emit radiation and gradually lose mass over time, effectively evaporating as they release energy. This process, although speculative, offers a solution to the information paradox by allowing black holes to release the information they absorb in a modified form. Planck stars could thus provide a new way of thinking about the life cycle of black holes, showing that they are not eternal, but rather temporary features in the cosmic landscape. The influence of black holes on star formation and galaxy evolution is another area that has captured scientists' attention. When black holes consume matter, they often release powerful jets of energy that can extend for thousands of light years. These jets can compress gas clouds, triggering bursts of star formation in nearby regions, while simultaneously heating gas in surrounding areas, preventing it from collapsing into new stars. This dual role means that black holes are both creators and regulators of stars within galaxies. Understanding how black holes interact with their host galaxies provides essential insights into the formation and development of galaxies, revealing that black holes play a fundamental role in shaping the universe as we know it. The discovery of intermediate mass black holes has opened a new window into understanding black hole evolution. Intermediate black holes, larger than stellar mass black holes but smaller than supermassive ones, have long been suspected to exist, but only recently have scientists been able to confirm their presence. These medium-sized black holes may represent an essential stage in the growth of supermassive black holes, offering clues about how black holes merge and accumulate mass over time. By studying intermediate black holes, scientists hope to trace the evolutionary pathway from small black holes to the massive giants at galaxy centers, piecing together a more complete picture of cosmic evolution. Finally, as our understanding of black holes expands, we are forced to confront the possibility that black holes might fundamentally alter our understanding of space and time. Some theories propose that the fabric of space-time itself is shaped by the presence and distribution of black holes, meaning that black holes could define the large-scale structure of the universe in ways we have yet to fully comprehend. This view suggests that black holes are not just objects within space-time, but are integral to the formation and dynamics of space-time itself. If true, this would mean that black holes are not merely cosmic outliers. They are foundational to the very existence of the universe, playing a role far more central and complex than previously imagined. As we continue to probe the mysteries of black holes, we find ourselves on the edge of knowledge, peering into realms that challenge our understanding of reality. Each discovery about black holes not only deepens our understanding of these strange objects, but also reveals new mysteries about the nature of the universe. Black holes embody the spirit of exploration, pushing us to expand our minds and embrace the unknown. They invite us to ponder questions about existence, time, and space that transcend the boundaries of science and philosophy alike. In the vastness of the cosmos, black holes stand as reminders that even the darkest regions of space are filled with secrets waiting to be uncovered. They inspire us to keep pushing the limits of knowledge, to seek answers to the questions that have captivated humanity for centuries, and to wonder at the beauty and complexity of a universe that is as mysterious as it is magnificent. The journey of discovery continues, and as we unlock more secrets of black holes, we come ever closer to understanding our place within this boundless, awe-inspiring cosmos. As we delve even deeper into the mysteries of black holes, we approach one of the most speculative yet thrilling ideas. Could black holes be the ultimate cosmic connectors, linking not only regions of space-time within our universe, but potentially connecting to other universes as well? Known as the multiverse hypothesis, this theory suggests that each black hole might serve as a bridge to an entirely separate cosmos, one with its own unique laws of physics and properties. This concept, grounded in certain interpretations of quantum mechanics and cosmology, suggests that black holes might function as portals, with each universe seeding new realities through its black holes. If this hypothesis is true, then black holes might represent points of cosmic genesis, birthing new universes in an endless, interconnected network of realities, each expanding and evolving in parallel to our own. The possibility of a multiverse connected by black holes gives rise to a profound implication, that each black hole could encapsulate a universe as vast and complex as our own. Just as we peer out at the cosmos from within our universe, creatures or entities within a universe inside a black hole might perceive their world as self-contained, unaware of the vastness outside. This recursive vision of reality challenges the way we think about existence, suggesting that every universe could be both unique and fundamentally connected to others through an infinite web of black hole networks. Each black hole in our universe could contain a new reality, and each black hole in that reality could, in turn, hold another universe, creating a nested structure of realities as intricate and infinite as the universe itself. Another cutting-edge area of research is the study of quantum hair on black holes. Traditionally, black holes were thought to be defined by only three properties: mass, charge, and spin, a principle known as the no-hair theorem. This theorem suggested that black holes have no other distinguishing features, and any information about objects that fell into them would be lost. However, recent theoretical advancements propose that black holes might possess a form of quantum hair, subtle features that encode information about everything that has fallen into them. This quantum hair could act as a record of each black hole's history, preserving information in a way that would allow it to be potentially recovered, thus offering a solution to the information paradox. If confirmed, the existence of quantum hair would revolutionize our understanding of black holes, showing that they are not merely blank slates, but cosmic archives with unique histories. The idea of black holes as information-preserving entities aligns with the holographic principle, which suggests that all the information contained within a black hole could be encoded on its two-dimensional surface. This principle may not only apply to black holes, but could extend to the universe itself, implying that everything we experience in 3 dimensions is a projection of information stored on a cosmic surface far beyond our perception. If the universe operates as a hologram, then black holes might play a central role in encoding and preserving information across the cosmos, effectively acting as cosmic memory banks. This idea transforms our view of black holes from mere gravitational traps to crucial components of a universe built on information, where every particle, wave, and interaction is a fundamental unit of data in a grand cosmic archive. The concept of entanglement and wormholes further extends the possibility that black holes could serve as conduits of cosmic information. In quantum mechanics, entanglement refers to the phenomenon where particles remain connected even when separated by vast distances, instantaneously affecting one another's states. Some scientists hypothesize that entangled black holes could be connected through wormholes, creating what is known as an Einstein-Rosen bridge. This would mean that black holes separated by galaxies or even across universes could be linked, transferring information instantaneously across the cosmos. If entangled black holes truly form such bridges, they could function as shortcuts through space-time, allowing for instantaneous travel or communication across unimaginable distances, a concept that could redefine our understanding of space, time, and connectivity in the universe. The role of black holes in the early universe also brings us to the idea of primordial black holes, thought to have formed shortly after the Big Bang. These black holes would be much smaller than those formed by collapsing stars, yet they could have significant mass. Some theories suggest that primordial black holes might make up a portion of dark matter, the invisible substance that forms the majority of matter in the universe. If primordial black holes are indeed a component of dark matter, studying them could unlock answers to one of the greatest mysteries in cosmology. Detecting primordial black holes would also provide insight into conditions in the universe's infancy, offering clues about how matter, energy, and structure emerged from the chaos of the Big Bang. As scientists investigate the potential for black holes to influence dark energy, we encounter the possibility that black holes might contribute to the accelerated expansion of the universe. While dark energy remains one of the least understood forces in the cosmos, some theories propose that black holes might serve as reservoirs for this mysterious energy, with their gravitational fields driving the expansion of space-time. If black holes are indeed involved in generating dark energy, it could mean that these enigmatic objects are integral to the large-scale evolution of the universe, shaping its destiny in ways that are only beginning to be understood. This connection between black holes and dark energy invites us to consider whether black holes play a role in cosmic balance, acting as both the engines and regulators of universal expansion. The concept of black holes as cosmic thermodynamic machines has also emerged as a compelling field of study. Black holes emit radiation, Hawking radiation, that slowly causes them to lose mass over incredibly long timescales. This radiation is a form of energy, suggesting that black holes adhere to the principles of thermodynamics, with entropy and temperature that change over time. The thermodynamic properties of black holes offer clues about the nature of time and entropy, potentially revealing why time flows in one direction and whether it might be reversible on a cosmic scale. By studying black holes, scientists hope to uncover a deeper understanding of thermodynamics, possibly even answering fundamental questions about the origins of time itself and the irreversible nature of physical processes in our universe. Another frontier of black hole research is the search for naked singularities. In general relativity, singularities, points of infinite density, are usually hidden behind an event horizon, the boundary beyond which nothing can escape. However, certain models suggest the existence of naked singularities, where these infinitely dense points are exposed without an event horizon. If naked singularities exist, they could provide an unprecedented glimpse into the fabric of space-time, allowing scientists to observe gravitational and quantum effects at their most extreme. Naked singularities would challenge our current understanding of the universe's laws, providing a window into the deepest mysteries of gravity, quantum mechanics, and the structure of reality itself. The discovery of black hole jets further expands our understanding of their influence on galactic evolution. As matter falls into a black hole, some of it is ejected in powerful jets that extend far beyond the host galaxy, releasing energy across thousands or even millions of light years. These jets can affect star formation, shape galactic clusters, and redistribute matter across vast regions of space. In this way, black holes act as cosmic sculptors, influencing the growth and structure of galaxies and regulating the formation of stars. By studying these jets, scientists gain insights into how black holes interact with their environment, revealing the intricate dance between creation and destruction that defines their role in the cosmos. The future of black hole research holds promises as we develop even more sophisticated methods of observation. The planned launch of gravitational wave detectors in space, such as the Laser Interferometer Space Antenna, LISA, will allow us to detect mergers of supermassive black holes and study gravitational waves from sources across the entire observable universe. These advancements will let scientists observe cosmic events that occurred billions of years ago, offering a time capsule that reveals the universe's history and evolution through the lens of black hole interactions. Each discovery brings us closer to understanding the full impact of black holes on the cosmos, offering a glimpse into how these dark giants shape the universe over time. As we continue to study black holes, we find ourselves increasingly in awe of their complexity, their role in the evolution of galaxies, and their potential to reshape our understanding of existence. Black holes stand as profound enigmas that push the limits of science, challenging us to explore the frontiers of knowledge. They serve as symbols of the unknown, as cosmic paradoxes where gravity and quantum mechanics collide, revealing mysteries that go beyond the material to the very essence of space, time, and reality. In the vast darkness of space, black holes represent the ultimate pursuit of knowledge, inviting us to journey deeper into the unknown, to question the nature of existence, and to imagine possibilities that extend far beyond our current understanding. They remind us that the universe is filled with boundless mysteries, each discovery leading us to new questions, each question revealing the beauty and complexity of a cosmos that is, in essence, an endless invitation to explore. The study of black holes is a testament to humanity's enduring curiosity and drive to uncover the secrets of the universe, a quest that will continue to shape the future of science, philosophy, and our understanding of the infinite. As we dive even further into the enigmatic and captivating world of black holes, we reach one of the most revolutionary concepts: the idea that black holes could serve as gateways to understanding the very origin of our universe and the fundamental nature of reality. Some researchers have proposed that black holes might not just be remnants of massive stars, but could be linked to the conditions present at the birth of the cosmos. These theories suggest that studying black holes could offer insights into the Big Bang itself, revealing clues about how our universe sprang into existence, and perhaps providing evidence of what existed before time began. In this way, black holes might act as cosmic archives, holding secrets that stretch back to the dawn of everything. One particularly profound theory suggests that black holes might recycle matter and energy, playing a role in a cosmic cycle of creation and destruction. In this model, black holes eventually release the matter they consume, perhaps in a different form or even in another universe. This concept of cosmic recycling challenges the traditional view of black holes as ultimate endpoints, suggesting instead that they are integral to a larger cycle that sustains and renews the universe. The matter absorbed by black holes might be ejected in a highly altered state, perhaps forming the seeds of new stars, galaxies, or even entire universes, contributing to an endless process of cosmic rebirth. The possibility that black holes might contain baby universes is another idea that has captivated cosmologists. According to this hypothesis, each black hole could spawn a new universe within it, with its own unique set of physical laws and constants. This idea aligns with certain interpretations of the multiverse, proposing that our universe may exist within a black hole in a higher dimensional realm. If true, this theory would mean that our universe itself is part of a vast family tree of universes, each one born from the gravitational collapse of another. In this grand cosmic structure, black holes are not just celestial oddities, but the very wombs of creation, constantly birthing new realms of existence. Another speculative yet intriguing idea is that black holes could act as time capsules in space-time, preserving information about the past and potentially even allowing us to peer back into ancient eras of cosmic history. As objects fall into a black hole, they are stretched and compressed, and while they appear to vanish from our perspective, the information about them might be encoded on the event horizon or somewhere within the black hole itself. If we could somehow retrieve or interpret this information, we could unlock secrets about the early universe, including the conditions that led to galaxy formation, star birth, and even the origins of life-supporting planets. Black holes could thus serve as cosmic historians, preserving the universe's memories in ways we have only begun to imagine. The study of black holes has also led scientists to explore the boundaries of causality, the relationship between cause and effect in the universe. Near the event horizon of a black hole, time behaves in strange and unpredictable ways, creating conditions where our usual understanding of past, present, and future may no longer apply. Some physicists theorize that black holes could distort time so dramatically that they might enable forms of backward causality, where effects precede causes. This phenomenon, while hypothetical, opens fascinating questions about the nature of time itself, including whether it might be possible to influence events across time or even communicate across temporal boundaries. Such theories push the very limits of science, suggesting that black holes might hold answers to questions about the ultimate nature of time, causality, and perhaps even free will. The recent detection of gravitational waves has further expanded our understanding of black holes, allowing us to observe their dynamic interactions in real time. Gravitational waves are ripples in space-time produced by massive cosmic events, such as the collision and merger of black holes. These waves provide a way to listen to the universe, capturing signals from events that occurred billions of years ago. By analyzing gravitational wave data, scientists can measure the mass, spin, and even the possible environment of merging black holes. This new window into black hole behavior has already led to the discovery of black holes in unexpected sizes and configurations, challenging our understanding of how these cosmic giants form and evolve. With each detection, gravitational wave astronomy brings us closer to a comprehensive view of black holes, revealing patterns and structures that shape the cosmos on the grandest scales. As we explore the relationship between black holes and dark matter, we find another intriguing mystery. Some scientists propose that black holes, particularly primordial black holes, might be responsible for at least a portion of the dark matter in the universe. Dark matter, an invisible form of matter that exerts gravitational influence but does not emit or absorb light, remains one of the greatest enigmas in cosmology. If black holes account for some dark matter, they could offer insights into the composition and distribution of this mysterious substance. Primordial black holes, if they exist, would have formed in the chaotic early universe and might be scattered throughout space, influencing galaxies and clusters without emitting light. Detecting these ancient black holes could revolutionize our understanding of dark matter, revealing a hidden structure within the universe that has remained invisible for billions of years. The study of black holes also invites us to reconsider our understanding of energy conservation on cosmic scales. The immense gravitational forces generated by black holes have led some scientists to propose that black holes might be capable of borrowing energy from the fabric of spacetime itself. This concept, although speculative, suggests that black holes might extract energy from the surrounding universe, perhaps even influencing the expansion rate of spacetime. If black holes can indeed tap into the universe's background energy, they could have implications for the conservation of energy on a cosmic scale, challenging our conventional understanding of physics. This theory would mean that black holes are not merely passive consumers of matter and energy, but active participants in the larger processes that govern the universe's structure and evolution. The notion that black holes could influence cosmic inflation, the rapid expansion of the universe shortly after the Big Bang, adds another layer of complexity to their role in cosmology. Some models propose that black holes or black hole-like structures might have existed in a pre-Big Bang state, influencing the initial conditions that led to cosmic inflation. If black holes contributed to the energy or matter distribution in the early universe, they could have played a role in setting the stage for the creation of galaxies, stars, and planets. This idea suggests that black holes might be linked not only to the formation of structure within the universe, but also to the very processes that made our universe habitable. In the field of quantum mechanics, black holes have introduced a wealth of paradoxes and unsolved mysteries, particularly regarding the nature of information. According to the no-hair theorem, black holes were once thought to lack distinguishing features, erasing all information about objects that fall into them. However, recent theories propose that information might be stored on a black hole's event horizon, encoded in tiny quantum states or bits. This idea aligns with the holographic principle, implying that a black hole surface could contain a complete record of everything that has ever fallen into it. If black holes do indeed store information, they could be the key to a new understanding of quantum information, potentially leading to breakthroughs in quantum computing and other technologies. As we continue to develop new technologies, our ability to study black holes will only improve. Space-based telescopes, advanced gravitational wave detectors, and particle accelerators will allow scientists to explore the properties of black holes with unprecedented precision. The next generation of observatories, including the James Webb Space Telescope and the upcoming Einstein Telescope, will enable us to observe the environment around black holes in greater detail, studying the effects of their immense gravity on surrounding matter and radiation. These advancements promise to uncover even more surprises, revealing unknown aspects of black holes that will continue to deepen our understanding of these cosmic enigmas. Black holes, in their silent and invisible way, offer us a pathway to exploring the ultimate questions about existence, reality, and the universe itself. They push us to think beyond the boundaries of known science, to embrace the mysteries that lie beyond the reach of observation, and to recognize that our journey of discovery is far from complete. Each new insight about black holes not only expands our knowledge of the cosmos, but also reveals how little we truly know, inviting us to continue exploring with curiosity and wonder. In the end, black holes are far more than cosmic oddities. They are profound mysteries that lie at the very heart of the universe, serving as bridges between the known and the unknown. They remind us that in the depths of space, there is always something more to discover, that the quest for knowledge is as endless as the universe itself. Black holes inspire us to keep reaching for answers, to venture into the unknown with courage, and to imagine a universe filled with infinite possibilities. With every discovery, black holes draw us closer to the profound realization that we are part of a cosmos as mysterious as it is boundless, a place where the journey of exploration will continue for as long as we dare to ask the questions that lie beyond the stars. As we journey deeper into the profound mysteries of black holes, we encounter the remarkable idea that these cosmic giants might hold clues to the nature of quantum gravity, the long-sought theory that aims to unify general relativity and quantum mechanics. Black holes exist at the intersection of these two realms. They are incredibly massive, invoking the gravitational effects described by Einstein's relativity, yet their interiors reach scales so minuscule that quantum effects dominate. This clash of theories at the heart of black holes presents scientists with a unique opportunity to explore quantum gravity in action, pushing us closer to a unified understanding of the universe. If black holes can reveal even a fragment of this elusive theory, it could lead to a revolution in physics, offering insights into the true nature of space-time, matter, and even the fabric of reality itself. One promising approach to quantum gravity in black holes involves the idea of loop quantum gravity. Unlike string theory, which posits that particles are made of tiny vibrating strings, loop quantum gravity suggests that space-time itself is composed of discrete, finite loops. In this theory, black holes are not smooth, continuous entities, but are instead formed of countless loops that replace the traditional singularity with a finite, dense core. If loop quantum gravity accurately describes black holes, it could mean that the crushing singularity does not exist as previously imagined. This theory would redefine the structure of black holes, suggesting they have a core made up of quantum loops rather than a point of infinite density, offering a possible solution to the information paradox and shedding light on the fundamental nature of space and time. The possibility that black holes might emit a form of information radiation beyond Hawking radiation is another fascinating concept. Traditional black hole theory suggests that black holes radiate energy in the form of Hawking radiation, which eventually causes them to evaporate over time. However, new research proposes that black holes could emit additional types of quantum information as they evaporate, allowing them to release stored information about everything that has fallen into them. If true, this would mean that black holes are not information destroyers, but rather cosmic processors that transform and release information back into the universe. This idea could bridge the gap between quantum mechanics and relativity, showing that black holes are dynamic, information-preserving entities rather than passive absorbers of matter and energy. Another intriguing hypothesis is that black holes might serve as cosmic stabilizers, helping to regulate the large-scale structure of the universe. Supermassive black holes, in particular, appear to play a central role in galaxy formation and stability. By generating powerful jets and winds, black holes can influence the distribution of gas within galaxies, regulating star formation, and even impacting the size and shape of galactic clusters. This feedback mechanism implies that black holes are not merely disruptive forces, but rather essential components of a balanced cosmic ecosystem. Without black holes acting as regulators, galaxies might collapse or grow uncontrollably, leading to an entirely different structure for the universe. In this view, black holes are essential to cosmic equilibrium, playing a role akin to cosmic anchors that maintain the structure and stability of galaxies. As we look even further into the possibilities, we encounter the notion that black holes could have direct interactions with other dimensions, as suggested by certain models in string theory and brane cosmology. These theories propose that our universe may be one of many branes, higher dimensional structures, floating within a larger multiverse. Black holes, with their intense gravitational pull, might be able to poke into these other dimensions, potentially transferring matter and energy between different realms. This concept suggests that black holes might not be isolated within our universe, but could act as bridges between dimensions, transferring energy or information across unseen realms. Such an idea would fundamentally alter our understanding of black holes, turning them into cosmic gateways that interact with realities beyond our perception. The potential for black holes to serve as cosmic clocks presents another fascinating avenue of exploration. Due to the extreme gravitational fields near black holes, time dilates significantly, meaning that time passes more slowly near a black hole compared to regions farther away. In theory, if an advanced civilization could harness this effect, they might use black holes to slow down or accelerate their perception of time. This time dilation effect could serve practical purposes in the distant future, allowing for methods of long-term data storage, or even experiments that require extended periods without significant time passing. Black holes, in this sense, could be more than cosmic mysteries. They might one day be utilized as tools to manage and manipulate time on an unprecedented scale. One of the most profound mysteries surrounding black holes is the potential they hold for revealing what lies beyond the observable universe. Since nothing can escape a black hole's event horizon, black holes are thought to hold regions that are inaccessible to outside observers. However, if theories about wormholes and Einstein-Rosen bridges are correct, black holes could offer a way to peer into other parts of the cosmos that are otherwise beyond our reach. This would mean that black holes are not isolated regions, but instead are linked to hidden sectors of the universe, connecting distant points across space-time. By studying black holes, we might uncover clues that point to the structure of the universe beyond the limits of what we can currently observe, revealing a vast cosmic landscape that remains hidden behind the event horizon. Another extraordinary concept is that black holes might serve as energy reservoirs, storing vast amounts of gravitational and kinetic energy that could potentially be harnessed. The rotational energy of a spinning black hole, for example, is believed to be immense, and certain processes, like the Penrose process, could theoretically allow particles to extract energy from a rotating black hole. This concept, while currently theoretical, suggests that black holes could be more than passive objects. They might serve as powerful sources of energy that could one day be tapped by advanced civilizations. If humanity could find a way to access and harness this energy, black holes could become sources of nearly limitless power, fueling space exploration and technological advancements on a scale previously unimaginable. In recent years, the study of extreme gravity has opened new perspectives on black hole interiors. Extreme gravity refers to the intense gravitational fields that occur near black holes, where space-time is warped to its limits. By understanding how particles and fields behave under these extreme conditions, scientists hope to gain insight into the fundamental structure of space-time and to explore whether there are undiscovered forces or particles that interact only under such intense gravity. The study of extreme gravity within black holes could reveal new physics that only becomes relevant in these extraordinary environments, providing a glimpse into aspects of nature that lie beyond our everyday experience. As our tools and technologies advance, scientists are developing increasingly sophisticated ways to study black holes indirectly. For instance, the Event Horizon Telescope, EHT, which captured the first ever image of a black hole silhouette, has demonstrated the power of combining radio telescopes around the globe to create an Earth-sized virtual telescope. With continued advancements, EHT and similar projects could provide even sharper images of black holes, allowing us to observe finer details of the regions near their event horizons. These observations could confirm or challenge existing theories, providing visual evidence of how matter and energy behave under extreme gravity. As technology progresses, we may even achieve the capability to observe the formation of black holes in real time, capturing the dynamic processes that lead to their birth. The mysteries surrounding black holes remind us that our journey of discovery is an open-ended one, filled with questions that defy simple answers. Black holes represent the ultimate challenge to human understanding, inviting us to question not only the nature of the universe, but the limits of our own perception. Each new discovery brings us face to face with the unknown, expanding our sense of wonder and inspiring us to keep exploring, keep questioning, and keep imagining. In the vast, boundless expanse of the cosmos, black holes stand as profound symbols of both destruction and creation, as forces that dismantle matter, yet may also give rise to new realms of possibility. They beckon us to peer into the heart of darkness, where reality itself is stretched, twisted, and redefined. Black holes are both destinations and doorways, luring us to the edges of knowledge and urging us to step forward into the mysteries that lie beyond. As we continue to study black holes, we may one day discover that they hold the answers to questions we have not yet even asked. In their silent, enigmatic presence, black holes invite us to ponder, to imagine, and to embrace a universe filled with wonders that extend beyond our wildest dreams. In the darkness of space, black holes shine as beacons of curiosity, reminding us that the pursuit of knowledge is infinite, as vast and as awe-inspiring as the cosmos itself. As we venture ever further into the profound mysteries of black holes, we reach a concept that may redefine our understanding of existence itself. The idea that black holes could serve as cosmic archives for the entire history of the universe. According to the holographic principle, which suggests that all information about three-dimensional objects can be encoded on a two-dimensional surface, black holes might function as cosmic libraries, preserving every piece of information about the matter and energy that falls into them. This would mean that black holes are not voids of lost matter, but rather storages of cosmic memory, encoding the essence of every star, planet, and particle that crosses their event horizons. If this theory holds, black holes could act as universal record keepers, preserving the stories of entire galaxies within their depths. The concept of black holes as cosmic archives ties into another revolutionary idea, that they may encode not only information about objects within our universe, but perhaps also data from alternate realities. This idea, sometimes linked to the multiverse hypothesis, proposes that black holes might connect to other realms, preserving information from universes that follow different physical laws. In this model, black holes could act as nodes within a vast network of realities, each black hole storing a fragment of the multiverse's history. This would mean that black holes are not merely structures within a single universe, but are integral parts of a larger, interconnected tapestry of existence, hinting at a cosmic web that spans realms beyond our own. Another intriguing aspect of black hole research involves the possibility of holographic duality, which suggests that black holes could help us understand how gravity and quantum mechanics might be unified. According to this principle, the gravitational behavior within a black hole's three-dimensional space could be represented by quantum fields on its two-dimensional boundary. If this duality holds, it would mean that every particle, wave, and field inside a black hole has a counterpart encoded on its surface, potentially allowing us to describe the internal workings of a black hole in purely quantum terms. This approach could bridge the gap between gravity and quantum mechanics, bringing us closer to a unified theory that explains the forces shaping our universe. The concept of black holes as potential time loops adds another layer of complexity to our understanding of these objects. Near the event horizon of a black hole, time behaves in ways that defy conventional understanding. According to relativity, time slows down dramatically near a black hole, and some theories even suggest that black holes could create closed time-like curves, essentially, loops in time that allow events to influence both their past and future. This would mean that an object falling into a black hole might experience a series of events that repeat indefinitely, as if trapped in a temporal cycle. Such time loops could theoretically allow for retrocausality, where an effect influences its cause, challenging our very notions of linear time and causality. If black holes indeed create these loops, they might hold the key to understanding time itself, revealing that the universe operates in cycles rather than in a straight line. One of the most profound questions in black hole physics today is the nature of the singularity at their core. Traditionally, a black hole singularity is thought to be a point of infinite density where space-time curves infinitely, causing all known laws of physics to break down. However, recent theories propose that singularities might not be true infinities, but instead quantum cores, where space-time is densely packed yet finite. These quantum cores could function as ultra-compressed states of matter, where particles exist in forms unknown to current science. If black holes indeed contain these quantum cores, they could reveal entirely new states of matter and energy, offering insights into physics beyond the standard model. This idea challenges the traditional view of black holes as entities with inescapable points of infinite density, instead presenting them as gateways to new, unexplored physical realms. The study of black holes has also inspired a closer examination of quantum entanglement and its role in space-time structure. In quantum mechanics, entanglement is a phenomenon where particles become linked such that the state of one particle affects the state of another, even if they are separated by vast distances. Some scientists believe that entanglement could be a fundamental component of space-time itself, with black holes acting as entanglement hubs that bind different regions of the universe together. If black holes indeed facilitate entanglement on a cosmic scale, it would suggest that reality is a vast web of interconnected particles, with black holes playing a critical role in maintaining the structure of space-time. This idea could transform our understanding of distance, suggesting that space is not merely a passive void, but an active, interconnected network where everything influences everything else, with black holes as central nodes in this cosmic web. Black holes are also driving new explorations into the nature of entropy, the measure of disorder in a system. In classical thermodynamics, entropy always increases, defining the arrow of time as a one-way path. However, black holes possess a unique form of entropy proportional to their surface area, rather than their volume. This property has led scientists to propose that black hole entropy might be the key to understanding why time flows in one direction. The relationship between a black hole's entropy and its event horizon suggests that black holes might act as thermodynamic engines, where matter and energy enter in a disordered state, potentially emerging in a different form over immense timescales. If black hole entropy is indeed linked to the arrow of time, these cosmic giants could provide answers to one of humanity's oldest questions: why time seems to move forward, and whether this forward motion is fundamental to the universe. As we study black holes, we also uncover fascinating insights into the formation of galaxies. Most large galaxies, including our Milky Way, host a supermassive black hole at their center. These black holes are thought to influence the growth and structure of galaxies, regulating star formation through the energy and radiation they emit. This feedback process, where black holes expel jets and winds, can heat surrounding gas, preventing it from collapsing into new stars. By moderating the rate of star formation, black holes essentially shape their galaxies, creating the complex and diverse structures we observe across the universe. Without these central black holes, galaxies might evolve very differently, suggesting that black holes are essential to the existence of galaxies as we know them. The possibility that black holes might create gravitational waves capable of carrying information across vast distances has opened a new realm of observational astronomy. Gravitational waves, which are ripples in space-time caused by massive events like black hole mergers, provide scientists with a way to listen to the universe. Since the first detection of gravitational waves in 2015, researchers have observed numerous black hole mergers, capturing signals that reveal their masses, spins, and collision dynamics. This new method of observation has unveiled the surprising prevalence of black hole mergers, suggesting that black holes are more common and active than previously thought. By studying gravitational waves, scientists are gaining insights into the life cycles of black holes, uncovering patterns and structures that deepen our understanding of their role in cosmic evolution. The idea that black holes might eventually evaporate through Hawking radiation, releasing their mass over eons, raises the possibility that they have finite lifespans. This gradual process would mean that black holes are not eternal. Instead, They evolve and change over billions or even trillions of years. As they emit Hawking radiation, black holes lose energy, shrinking until they vanish in a final burst of radiation. This process introduces a sense of cosmic mortality to black holes, suggesting that even the universe's most mysterious and enduring objects are part of a larger cycle of birth, growth, and eventual decay. If black holes indeed evaporate, they could contribute to the distribution of matter and energy in the universe's final stages, potentially playing a role in the heat-death scenario where entropy reaches a maximum and the universe reaches thermodynamic equilibrium. In the realm of speculative yet thrilling possibilities, some scientists have proposed that black holes might be artificial objects created by advanced civilizations, known as Kardashev Type 3 civilizations. These hypothetical societies could harness black holes as energy sources, storage systems, or even computing machines. By tapping into the immense rotational and gravitational energy of black holes, such civilizations might use them as cosmic engines, driving technologies far beyond our comprehension. This idea challenges our perceptions of black holes as natural objects, suggesting that they might be manipulated or even constructed by intelligent beings in distant parts of the universe. If we ever detect signs of artificial manipulation around black holes, it would suggest that life in the universe can achieve levels of technological sophistication that transcend anything we can currently imagine. Ultimately, black holes invite us to confront the profound mystery of existence itself. They challenge the limits of our understanding, pushing us to explore realms of physics, time, and space that defy traditional boundaries. With each discovery, black holes expand our sense of wonder, reminding us that the universe is an unending frontier filled with secrets beyond our reach. They inspire us to look deeper, to question more, and to imagine possibilities that stretch the limits of our imagination. In their silent darkness, black holes beckon us toward the unknown, urging us to embrace the mysteries that lie at the heart of the cosmos. As we continue our journey of exploration, black holes remind us that knowledge is not a destination, but a path that leads us ever further into the vast, awe-inspiring reaches of the universe. Each step brings us closer to understanding our place in the cosmos, a reminder that the quest for truth is as infinite and boundless as the stars themselves. As we delve even deeper into the mysteries of black holes, we encounter a concept that has the potential to alter our perception of reality itself. The possibility that black holes might be seeds from which entire universes are born. According to certain interpretations of cosmology, a black hole's singularity might not signify the end of space and time, but rather the beginning of a new cosmos. This theory, known as black hole cosmology or the Fecan universe hypothesis, suggests that every black hole could generate a new universe within it, with its own unique physical laws and constants. This concept leads to a vision of a multiverse, where each black hole serves as a gateway to a new universe, endlessly branching out like a cosmic tree with infinite roots and branches. In this framework, our own universe might be the product of a black hole in another, older universe, making black holes the primary mechanism of creation in a multiverse that perpetually renews itself. This self-replicating structure implies that black holes are more than mere endpoints. They are powerful engines of cosmic regeneration, continuously spawning new realms with variations in their fundamental properties. If this theory holds true, black holes could represent both the death of stars and the birth of universes, giving them a dual role as cosmic endings and beginnings. This idea of black holes as cosmic birthplaces leads us to consider another groundbreaking concept: that each universe created within a black hole might inherit certain traits from its parent universe, similar to biological inheritance. In this scenario, universes that produce more black holes are more likely to pass on their genetic material to subsequent universes. Over time, this process of cosmic natural selection could lead to a multiverse where universes with physical laws that favor black hole formation become more common. This model, sometimes referred to as the evolutionary universe hypothesis, suggests that our universe's physical constants, such as the strength of gravity or the mass of elementary particles, might be fine-tuned not by coincidence, but through a process of natural selection across universes. If this is the case, then black holes play a pivotal role in shaping the very laws that govern each universe, suggesting a grand, self-organizing structure underlying the multiverse. The study of black holes has also inspired an examination of causal structures in spacetime, leading to the concept of closed time-like curves, CTCs. CTCs, theoretical loops in spacetime, allow for paths where an object could return to its own past, theoretically enabling forms of time travel. While CTCs remain purely hypothetical, black holes, with their intense gravitational fields, are considered one of the few places in the universe where CTCs might exist. Near the event horizon of a rotating black hole, known as a Kerr black hole, spacetime twists and curves in such a way that closed loops in time might be possible. This raises the question of whether black holes could allow for backward causality, where future events could influence the past. If such time loops exist, they would defy our linear understanding of cause and effect, suggesting that black holes might not only reshape space but also challenge the very nature of time. As we explore black holes further, the idea of black hole thermodynamics emerges as a cornerstone of understanding these cosmic phenomena. Stephen Hawking's discovery of Hawking radiation showed that black holes are not entirely black. They emit radiation due to quantum effects near the event horizon. This emission of radiation implies that black holes have a temperature and can lose mass over time, eventually evaporating. However, black hole thermodynamics also implies that black holes have entropy, a measure of disorder, which is directly proportional to the surface area of their event horizon rather than their volume. This relationship between entropy and area, known as the Bekenstein-Hawking entropy, suggests that information about everything that has fallen into a black hole might be stored on its surface. This has profound implications for the nature of information itself, hinting that the universe might fundamentally operate as a hologram, where three-dimensional information is encoded on two-dimensional surfaces. This holographic perspective has led to the development of AD/CFT correspondence, a theoretical framework proposing that a gravitational system within a certain type of space, anti-de Sitter space, can be described by a quantum field theory without gravity on its boundary. While our universe does not appear to be an anti-de Sitter space, this concept has become a vital tool in theoretical physics, offering insights into how gravity and quantum mechanics might coexist. If black holes embody a kind of holographic structure, it could mean that all the information about their interiors is encoded on their surfaces, potentially offering a way to reconcile the paradoxes between general relativity and quantum mechanics. This duality could bridge the gap between these two seemingly incompatible theories, transforming black holes from cosmic enigmas into the key to a deeper understanding of reality itself. Another fascinating development in black hole research involves the potential for black holes to produce echoes after merging. When two black holes collide, they create gravitational waves, ripples in spacetime that propagate outward and can be detected by observatories like LIGO and Virgo. Some scientists hypothesize that in certain situations, these gravitational waves might produce faint echoes, which could provide clues about the structure of spacetime near black holes. These echoes, if observed, could reveal whether black holes have smooth event horizons or if they possess a more complex, fuzzy boundary. Detecting echoes would provide unprecedented insights into the nature of black holes and could even hint at new physics beyond the standard model, challenging our assumptions about the smoothness of spacetime and the fundamental properties of black holes. The study of black holes has also pushed us to consider whether they might interact with dark matter, the invisible substance that makes up most of the universe's mass. Dark matter does not emit, absorb, or reflect light, making it detectable only through its gravitational effects. Some theories propose that black holes might accumulate dark matter, forming dense halos around them. This interaction could influence the evolution of galaxies, as the dark matter gathered by black holes might affect the distribution of stars and gas within galaxies. If black holes indeed attract dark matter, they could serve as focal points for studying this mysterious component of the cosmos, potentially leading to breakthroughs in our understanding of both black holes and dark matter. The potential for black holes to echo also raises questions about their stability. While traditional black holes are thought to have stable event horizons, new theories suggest that quantum effects could create firewalls or other structures at the horizon. If these structures exist, they would mean that black holes have more intricate surfaces than previously thought, potentially leading to detectable phenomena like echoes and gravitational waves. Observing such features could reveal a new layer of complexity in black holes, suggesting that their surfaces are dynamic and governed by principles that we have only begun to understand. As we continue to study black holes, we also confront the idea that they might hold answers to the nature of cosmic inflation, the rapid expansion of the universe in its first moments. Some scientists propose that the conditions within black holes could mirror those during the inflationary period, offering a natural laboratory for studying the forces that drove the early universe's expansion. If black holes do indeed contain regions of intense energy similar to those of the early universe, they could provide insights into how inflation occurred, revealing clues about the fundamental forces and particles that shaped the cosmos. Black holes could thus serve as windows into the universe's infancy, offering a glimpse of the conditions that led to the formation of galaxies, stars, and eventually life. In the search for a theory of everything that unites quantum mechanics and general relativity, black holes remain one of our best tools for testing new ideas. The extreme conditions near a black hole's singularity provide a natural testing ground for theories of quantum gravity, as they combine both strong gravitational fields and quantum effects. By studying how particles, fields, and space-time behave near black holes, scientists hope to uncover a unifying framework that explains all fundamental forces. This quest for a theory of everything is one of the most ambitious goals in physics, and black holes could hold the key to achieving it, potentially unlocking a new era of understanding that brings us closer to the core principles governing the universe. The allure of black holes lies in their ability to challenge and expand our understanding at every turn. They represent the ultimate boundary of human knowledge, where science meets mystery and where the very nature of reality is called into question. Each new discovery about black holes brings us closer to answers while also opening doors to new, deeper mysteries. Black holes invite us to explore not only the cosmos but also the limits of human imagination, pushing us to ask questions that transcend the boundaries of known science. In their dark and silent depths, black holes are far more than cosmic voids. They are the universe's most profound paradoxes, embodying both destruction and creation, order and chaos, mystery and revelation. They remind us that even in the vast reaches of space, there are realms we have yet to explore, questions we have yet to ask, and secrets waiting to be uncovered. Black holes inspire us to keep looking up, to keep questioning, and to keep seeking understanding in a universe that is as boundless and mysterious as our own curiosity. As we continue our journey of discovery, black holes remain our guides into the unknown, urging us forward into realms of knowledge and wonder that lie beyond our current understanding. They are cosmic milestones on the path of human inquiry, signposts marking the edge of what we know and the beginning of what we can only imagine. In the infinite darkness of space, black holes are beacons of curiosity, illuminating the path forward and inviting us to embrace the mysteries that define our universe. As we journey further into the vast mysteries of black holes, we encounter a concept that pushes the boundaries of science fiction into scientific speculation. The possibility that black holes could be pathways for advanced forms of communication or even cosmic travel. Theories suggest that black holes, specifically rotating or charged black holes, might contain wormholes, hypothetical tunnels through space-time that could connect distant points in the universe or even bridge entire universes. Known as Einstein-Rosen bridges, these theoretical wormholes could allow for instantaneous travel across unimaginable distances. If these wormholes exist, they could offer the potential for future space exploration on a scale previously relegated to the realms of imagination, with black holes acting as cosmic shortcuts through space-time. The idea of using black holes for interstellar or intergalactic travel remains speculative, but it has inspired researchers to investigate the properties of these theoretical wormholes. A rotating black hole, or Kerr black hole, may create a region where space-time twists so intensely that it forms a stable tunnel. If this tunnel could be navigated, it might enable travel from one part of the universe to another, bypassing the vast distances between stars or galaxies. The potential for black holes to serve as portals across the cosmos invites us to imagine a universe where travel through black holes could become a means of exploration. However, the intense gravitational forces and high-energy conditions near a black hole make this prospect immensely challenging, if not impossible, with current technology. Yet the idea continues to captivate, as it raises the tantalizing question of whether black holes could someday become the highways of the universe. In addition to serving as potential portals, black holes may also play a role in cosmic communication. Some scientists theorize that if particles or waves could survive the intense conditions near a black hole's event horizon, they might carry signals across great distances or even between universes. Known as quantum teleportation, this process involves transferring information instantaneously between entangled particles. Black holes, with their gravitational and quantum effects, might amplify or stabilize this process, allowing for a form of communication that defies conventional limits. While the idea is speculative, it opens the possibility that black holes could facilitate cosmic messaging systems, with signals encoded in the quantum states of particles. This potential for black holes to act as communication hubs between far-flung regions of space-time is a concept that sparks the imagination, hinting at the possibility of connecting with civilizations or regions of the universe far beyond our reach. Another emerging theory proposes that black holes could play a role in the quantum foam structure of space-time. Quantum foam, as theorized by physicist John Wheeler, describes space-time at the smallest scales as a turbulent sea of fluctuating energy and particles. Black holes, with their extreme gravitational fields, might influence this foam, shaping the structure of space-time in ways we don't yet fully understand. This interaction between black holes and quantum foam could reveal new insights into the quantum nature of gravity, providing clues about the fundamental fabric of the universe. If black holes can interact with quantum foam, they could serve as windows into the tiniest scales of reality, helping us to understand how space-time behaves under extreme conditions and possibly revealing connections between the macroscopic and quantum realms. The connection between black holes and cosmic inflation is another area of active research. Inflation refers to the rapid expansion of the universe that occurred fractions of a second after the Big Bang. Some theories suggest that black holes could contain regions where inflation-like processes are still occurring, creating baby universes within their depths. These inflating regions would theoretically expand at an accelerating rate, forming new universes with properties derived from the black hole that birthed them. If this theory is correct, black holes might not only represent the endpoints of stars but also the starting points of new universes, with each black hole containing a unique realm with its own physical laws. This would imply that black holes are fundamental to the cycle of cosmic creation, seeding new universes that continue to expand and evolve independently of our own. The idea that black holes might serve as incubators for new universes ties into the concept of cosmological natural selection. According to this theory, universes that produce more black holes are more likely to generate subsequent universes, leading to a multiverse where black hole-rich universes become increasingly common. This evolutionary model suggests that our universe might be fine-tuned to allow for black hole formation, not by coincidence, but through a process of cosmic selection across generations of universes. Black holes, in this view, are not just isolated objects but crucial players in a grand evolutionary scheme, shaping the conditions that make new universes possible. This vision of the multiverse, where each black hole seeds a new cosmos, transforms black holes from anomalies into essential agents of cosmic continuity. As we deepen our understanding of black holes, we are also forced to reconsider the nature of information in the universe. The information paradox suggests that information about objects falling into a black hole might be lost forever, violating principles of quantum mechanics that require information to be conserved. However, new research suggests that black holes might encode information on their event horizons, preserving it in ways we do not yet fully understand. Some scientists propose that black holes may store information holographically, encoding data in quantum bits or qubits on their surfaces. If true, this would mean that black holes act as cosmic repositories, preserving detailed records of every particle, wave, and interaction that has entered them. Black holes could therefore serve as vast archives, capturing the history of the universe in ways that remain invisible to us, but theoretically recoverable. The recent discovery of intermediate mass black holes has opened a new frontier in understanding black hole formation and evolution. While stellar mass black holes form from collapsing stars and supermassive black holes reside in galactic centers, intermediate mass black holes occupy a middle ground that has been challenging to observe. These black holes, believed to be hundreds to thousands of times the mass of our Sun, might represent the building blocks of supermassive black holes, forming through mergers of smaller black holes and accumulations of matter. Studying these intermediate mass black holes could reveal the processes that lead to the formation of galactic centers, offering clues about how supermassive black holes grew to their enormous sizes. These medium-sized black holes could also provide insights into the missing link in the evolutionary path of black holes, helping to complete the picture of how black holes evolve across cosmic time. As we advance in black hole research, the prospect of quantum black holes emerges, a type of black hole so small that it operates entirely within the realm of quantum mechanics. Quantum black holes, if they exist, would be incredibly tiny, perhaps on the scale of subatomic particles, and would behave in ways that blend gravity with quantum uncertainty. These minuscule black holes could offer a testing ground for theories of quantum gravity, allowing scientists to study black hole behavior at the intersection of quantum mechanics and relativity. If researchers can create or detect quantum black holes, it would revolutionize our understanding of black holes and quantum mechanics alike, revealing phenomena that bridge the divide between the macroscopic and microscopic worlds. The role of black holes in the potential end of the universe is another compelling topic. Some theories propose that black holes could contribute to the eventual heat death of the universe, a state in which entropy reaches a maximum and no usable energy remains. As black holes gradually evaporate through Hawking radiation, they release energy back into the universe, contributing to its eventual equilibrium. However, the evaporation process is incredibly slow, taking longer than the current age of the universe for most black holes to vanish. This cosmic timeline suggests that black holes could be among the final structures to exist in a universe heading toward thermodynamic equilibrium, marking a quiet but significant end to their life cycle. Black holes thus serve as the ultimate cosmic witnesses, enduring through epochs and outlasting stars, galaxies, and even the processes that sustain life. In the field of speculative physics, some researchers have proposed that black holes might enable forms of information resurrection, where the information that falls into a black hole could be retrieved through subtle quantum processes, known as quantum cloning. This process involves creating duplicate states of information that could survive even as the original object is absorbed by a black hole. If quantum cloning is possible, it would mean that information is not truly lost in black holes, but preserved in ways that we have yet to decipher. This notion challenges the very fabric of our understanding of information, suggesting that black holes might ultimately reveal methods for conserving and reconstructing data even under extreme conditions. Finally, as we expand our observational capabilities, we stand on the brink of an era where black holes may be studied in more detail than ever before. Next-generation gravitational wave detectors, such as the planned Laser Interferometer Space Antenna, LISA, will be able to observe the mergers of supermassive black holes across vast distances, capturing signals from billions of years ago. These observations will allow us to trace the history of black hole mergers, map the formation of cosmic structures, and witness events that have shaped the evolution of the universe. With space-based telescopes, high-energy observatories, and advanced computational models, scientists are poised to unlock secrets of black holes that have eluded us for centuries, potentially revealing new physics and transforming our understanding of the cosmos. As we continue this journey, black holes remind us that the universe is filled with mysteries that extend beyond the bounds of our current knowledge. They stand as symbols of the unknown, challenging us to stretch our understanding and embrace the profound complexities of the cosmos. With every discovery, black holes push the boundaries of science and inspire us to imagine new possibilities. They are cosmic enigmas that remind us that, in the vast tapestry of the universe, there are always new horizons to explore, new questions to ask, and new answers waiting to be found. In their dark and silent presence, black holes represent both the beginning and the end, the known and the unknowable, the finite and the infinite. They are portals to understanding, revealing truths about space, time, and reality that reshape our place in the cosmos. As we look deeper into these cosmic giants, we are drawn ever closer to the realization that the journey of discovery is as endless as the universe itself. In the shadow of black holes, we find the light of curiosity, beckoning us forward into the infinite mystery that defines our universe and our place within it. As we venture even further into the mind-bending realms of black hole science, we approach one of the most ambitious questions yet. Could black holes fundamentally change our understanding of reality itself, revealing truths about the structure of the universe that go beyond even our most advanced theories? Recent theoretical developments suggest that black holes may not just bend space and time. They could reveal the existence of additional dimensions beyond the familiar 3 dimensions of space and 1 of time. If black holes interact with extra dimensions, they could reshape our very conception of the cosmos, unveiling hidden aspects of reality that lie just beyond our current perception. Some researchers propose that black holes could leak gravitational energy into these extra dimensions, making them observable only indirectly through their effects on our universe. In certain theories, such as string theory and brain cosmology, our universe is a 3-dimensional brain embedded within a higher dimensional space. Black holes, with their immense gravitational fields, might reach across brains, creating shadows or distortions in adjacent dimensions. If such interactions exist, they could provide evidence for a multiverse of higher dimensional sheets or realities stacked together, with black holes serving as cosmic windows through which energy and information subtly pass between these realms. This possibility suggests that black holes are not only features of our universe, but could be intertwined with other dimensions, connecting us to realities we cannot yet perceive. The idea of black holes connecting to other dimensions also brings us to the concept of brain-world black holes. In certain models, black holes might form at the intersection points of multiple brains, creating regions where the physics of multiple universes overlap. These brain-world black holes could possess unique properties, potentially allowing information to cross between brains, creating echoes or anomalies that we might detect in our own universe. If we could identify signs of brain-world black holes, it would revolutionize our understanding of space-time, proving that black holes are more than objects within our universe. They are multidimensional gateways that blur the boundaries between different realities. This theory raises the question of whether we live in a multiverse brain populated by black holes that connect a tapestry of parallel worlds. Another breakthrough in black hole research has come from the study of black hole chaos. Chaos theory suggests that small changes in initial conditions can lead to wildly different outcomes, an effect often illustrated by the metaphor of a butterfly flapping its wings and causing a hurricane. In the context of black holes, chaos theory might apply to how matter and energy behave near the event horizon. According to recent studies, particles near a black hole's event horizon can exhibit chaotic behavior, where tiny perturbations create unpredictable effects. This chaotic dynamic could make black holes incredibly sensitive to surrounding conditions, responding to quantum fluctuations in unpredictable ways. If black holes are indeed chaotic systems, they might serve as natural amplifiers of quantum randomness, meaning that each black hole could behave in unique, irreproducible ways, fundamentally challenging our assumptions about determinism in the universe. Black hole chaos also ties into the butterfly effect in quantum mechanics, which suggests that small quantum changes could have vast impacts over time. Near a black hole, the butterfly effect might be magnified, with tiny quantum events at the edge of the event horizon potentially affecting large-scale structures within the black hole. If black holes can amplify quantum effects, they could represent a bridge between the microscopic and macroscopic worlds, where quantum fluctuations influence the behavior of massive objects. This concept could transform our understanding of quantum gravity, revealing that black holes operate as natural laboratories for observing how tiny quantum states impact vast cosmic scales. By studying black hole chaos, scientists may unlock clues about the fundamental randomness of the universe, exploring how the quantum and cosmic scales are deeply interconnected. As we continue to investigate black holes, the concept of black hole thermodynamics grows increasingly significant, offering insights into the relationship between entropy, temperature, and information. The discovery that black holes emit Hawking radiation, particles generated by quantum effects near the event horizon, has shown that black holes have a temperature and can lose mass over time. This process suggests that black holes are not isolated entities but thermodynamic systems that interact with their surroundings. According to the principles of thermodynamics, black holes also possess entropy, a measure of disorder, which increases as they absorb matter. This entropy is proportional to the surface area of the event horizon rather than the volume within, leading scientists to consider that all information about matter that falls into a black hole might be stored on its surface. If black hole entropy is linked to a deeper structure of reality, then black holes could embody the thermodynamic arrow of time, offering insights into why time flows in one direction and whether this flow is fundamental to the universe. The concept of black hole entropy also connects to recent theories on entropic gravity. Some physicists propose that gravity may not be a fundamental force, but rather an emergent property of entropy. In this view, black holes represent the highest concentrations of entropy, exerting a gravitational pull that results from the tendency of systems to move toward higher disorder. If gravity is indeed a byproduct of entropy, then black holes might be the ultimate expression of this entropic process, pulling matter inward not because of mass alone, but because of an underlying tendency toward disorder. This would mean that black holes are not merely regions of extreme gravity, but manifestations of entropy in its most concentrated form, connecting thermodynamics and gravity in a way that reshapes our understanding of both forces. The question of what lies at the heart of a black hole, traditionally thought to be a singularity, continues to spark debate. A singularity is a point of infinite density where space-time curves infinitely, but many scientists now believe that singularities might not actually exist. Instead, certain quantum theories propose that black holes contain quantum cores or Planck stars at their centers, where matter is compressed to an extreme but finite density. These quantum cores could replace the singularity with a region governed by quantum mechanics, preventing infinite density and preserving information in some unknown form. If black holes contain such quantum cores, they might act as reservoirs of ultradense, exotic states of matter, potentially revealing a new phase of matter and energy that only exists within black holes. This theory implies that black holes are not points of absolute collapse, but complex structures with unique inner realms, transforming our view of what happens when matter reaches the end of its journey. The study of black holes has also inspired the idea of holographic cosmology, which proposes that the entire universe might function as a hologram, with all information encoded on a two-dimensional boundary. In this model, black holes would be central to understanding how our three-dimensional reality emerges from two-dimensional data. The holographic principle suggests that every particle, wave, and field within a black hole's volume could be represented by information encoded on its surface. If this principle applies to the universe as a whole, then black holes are not just cosmic objects but fundamental units of a larger, holographic structure, where all of reality is a projection of information. This theory could explain how black holes manage to encode information about everything they absorb, aligning with quantum mechanics and potentially offering a solution to the information paradox. Black holes, in this holographic view, serve as microcosms of the universe, encoding data in ways that might be unlocked with future technology. The possibility of quantum entanglement across black holes introduces yet another groundbreaking idea. Quantum entanglement is a phenomenon where particles remain connected such that the state of one particle instantly affects the state of another, regardless of distance. Some scientists speculate that black holes might be entangled with one another across vast distances, creating an entanglement network that links different regions of the universe. This network could allow for information to be transferred between black holes in ways that transcend ordinary space-time, creating a web of connections that binds the cosmos together. If black holes are indeed entangled across the universe, they might act as the nervous system of the cosmos, linking distant regions in a complex, invisible network of quantum connections. This entanglement would mean that black holes are not isolated phenomena, but are integral to the universe's interconnected structure. Finally, the discovery of black hole superradiance adds another layer of mystery. Superradiance is a process where particles or waves that interact with a rotating black hole can extract energy from it, amplifying their intensity. This effect could mean that black holes are not merely passive objects but energy sources capable of amplifying certain types of particles. Superradiance might even allow for the theoretical extraction of rotational energy from black holes, opening up the possibility of tapping into black holes as power sources. While currently theoretical, this concept suggests that black holes could become resources for future civilizations, offering nearly limitless energy drawn from the rotation of supermassive black holes in galaxies. If we ever find a way to harness superradiance, black holes could be transformed from cosmic mysteries into valuable resources, supporting future technologies and even interstellar exploration. As we continue to explore the mysteries of black holes, we find that each discovery reshapes our understanding not only of these cosmic giants, but of the universe itself. Black holes challenge our perceptions of space, time, matter, and even information, pushing us toward questions that lie at the edge of known science. They remind us that the universe is vast, intricate, and full of secrets waiting to be uncovered. Every insight into black holes brings us closer to understanding the fabric of reality, revealing layers of complexity that hint at a universe far richer than we ever imagined. In the endless quest to understand black holes, we are reminded that science is a journey, not a destination. Black holes beckon us to explore, to question, and to imagine a universe where the boundaries between reality, time, and space are fluid and ever-changing. They are symbols of the unknown, marking the frontier of human knowledge and inspiring us to reach beyond what we can see, touch, or measure. In their silent, enigmatic depths, black holes hold the promise of discovery, inviting us to embrace the mysteries that lie beyond the stars and to continue the journey of exploration that defines us as a species. As we delve yet deeper into the astonishing mysteries surrounding black holes, we approach one of the most captivating ideas in modern physics. Could black holes act as cosmic recyclers, converting matter and energy into new forms and releasing them back into the universe in ways we cannot yet detect or understand? According to emerging theories, black holes might not be final endpoints for the matter they consume. Instead, they could transform and reprocess this material, perhaps releasing it as strange forms of radiation, or even converting it into exotic particles that escape detection. This concept challenges the traditional view of black holes as insatiable cosmic traps, suggesting that they might play a more dynamic role in the cosmic ecosystem. One of the key ideas fueling this notion is the study of black hole evaporation. Through Hawking radiation, black holes slowly lose mass, releasing particles that gradually erode their mass over eons. This process suggests that black holes do not retain everything indefinitely. Instead, they return some fraction of the absorbed material back to the universe, albeit in altered form. If this theory holds, black holes could be viewed as complex engines that process matter and energy, converting them over long time frames. The complete evaporation of a black hole, although unimaginably distant in the future, would theoretically release all the information it had consumed, suggesting that black holes, rather than obliterating matter, are part of a continuous cycle of transformation and release. This notion of cosmic recycling opens up the idea of white holes, the hypothetical opposites of black holes. While a black hole draws matter in, a white hole would expel it, theoretically emitting all the material it had absorbed. Some theories propose that white holes could be linked to black holes, with matter that falls into a black hole, eventually emerging from a white hole in another part of the universe, or even in another universe entirely. If white holes exist, they could act as outlets for matter and energy that black holes absorb, suggesting a cosmic balance between these two entities. This concept also raises the tantalizing possibility that black holes and white holes are part of a vast cosmic circulation system, where matter and energy are continuously cycled, conserved, and redistributed. The idea that black holes could be portals to other parts of the universe or to other universes altogether leads us to explore the concept of multiversal black holes. In this model, black holes serve as gateways not merely between distant points within our universe, but across a multiverse, connecting realms that operate under different physical laws. This speculative theory suggests that each black hole might contain a universe within it, or that it could link our universe to others, forming a network of interconnected cosmoses. If true, this would mean that black holes are not isolated phenomena, but integral nodes in a vast, multiversal web, allowing for the possibility of energy or even information exchange across realities. The study of space-time foam further complicates our understanding of black holes. Space-time foam refers to the quantum fluctuations occurring at the smallest scales of reality, where space-time is thought to be frothy and turbulent, filled with tiny, transient black holes and wormholes. Some scientists theorize that black holes could interact with this foam, influencing quantum states across the universe. This interaction could mean that black holes are not merely structures within space-time, but actively shape the space-time fabric itself, impacting the behavior of particles and fields at quantum scales. If black holes do influence space-time foam, they could play a role in sustaining the structure of the universe, stabilizing it at the quantum level in ways we do not yet understand. Another radical concept that has emerged from black hole research is the possibility of cosmic censorship. According to the cosmic censorship conjecture, the universe hides certain extreme phenomena, such as singularities, behind event horizons, preventing them from being directly observed. If true, this means that black holes serve as cosmic screens that shield us from the most extreme and incomprehensible regions of physics. This raises philosophical questions about the nature of knowledge itself. Are black holes fundamentally unknowable? Do they serve as boundaries to human understanding, marking the limits of what we are capable of observing? If cosmic censorship holds, then black holes represent the ultimate hidden reality, a place where the laws of physics might be radically different, forever concealed from direct observation. The notion that black holes could act as cosmic screens also leads us to the theory of fuzzballs, proposed in string theory. According to the fuzzball model, black holes might not contain singularities at all. Instead, they could be composed of vast, tangled strings that form a fuzzy structure, replacing the traditional point of infinite density with a network of interacting strings. In this model, black holes are complex, structured objects rather than simple voids, with each fuzzball encoding detailed information about everything that falls into it. If the fuzzball theory is correct, it would mean that black holes have a rich internal structure governed by quantum principles, challenging the idea of a featureless singularity and suggesting that black holes could be studied and understood at a deeper level. The potential for black holes to influence time itself adds yet another layer of intrigue. Near a black hole's event horizon, time dilates significantly, slowing to a near standstill from the perspective of an outside observer. This effect leads to fascinating possibilities, particularly in terms of long-term information storage or even preservation. In theory, a civilization could position information near the event horizon of a black hole, preserving it in slow time for billions or trillions of years. This effect could allow black holes to act as cosmic time capsules, preserving data for future generations or even civilizations yet to emerge. If this concept could be harnessed, black holes might one day serve as repositories for vast amounts of knowledge, acting as libraries of cosmic information that withstand the ravages of time. The concept of black holes as time capsules intersects with theories about their role in the ultimate fate of the universe. If black holes continue to evaporate through Hawking radiation, they could eventually release all of their absorbed information, slowly dispersing their contents back into the universe. This process would take place over extraordinary timescales, longer than the current age of the universe, with black holes gradually fading and returning their energy to the cosmic background. In the distant future, black holes might be the last remnants of structure in an otherwise dark and empty universe, releasing their contents in one final whisper of information as the cosmos approaches thermodynamic equilibrium. In this way, black holes might serve as cosmic witnesses, carrying the history of the universe within them and releasing it as the universe enters its final stages. Another area of study is whether black holes could provide insights into the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. Some researchers propose that the intense gravitational fields around black holes could interact with dark energy in ways that we don't yet understand, possibly influencing the expansion rate of space-time. If black holes and dark energy are connected, then studying black holes could unlock clues about the fate of the universe itself, revealing whether expansion will continue indefinitely or if it might eventually slow down or reverse. Black holes, in this view, are not just points of gravitational collapse, but may play an active role in the universe's large-scale structure and evolution, helping to determine the ultimate destiny of everything within it. The idea of black holes as energy sources for advanced civilizations has also captured the imagination of scientists and science fiction writers alike. The concept of a Kardashev Type 3 civilization, a hypothetical civilization that harnesses energy on the scale of its entire galaxy, might involve the use of black holes as power sources. By tapping into the energy of a rotating black hole through a process like the Penrose process, where particles are accelerated and capture some of the black hole's rotational energy, such a civilization could potentially extract enormous amounts of energy. If humanity ever reaches a level of technological sophistication capable of harnessing black holes, it would represent a profound leap in our ability to explore and survive in space, with black holes acting as cosmic fuel stations that enable interstellar and perhaps intergalactic travel. Finally, the study of black holes continues to push the boundaries of what we understand about the very nature of existence. Each theory, each experiment, and each discovery brings us closer to grasping the underlying principles that govern reality, even as black holes reveal ever deeper mysteries that challenge our understanding. They remind us that, in the vast expanse of the universe, there is always something more to learn, something more to question, and something more to explore. Black holes are not only objects of scientific fascination, they are symbols of the unknown, markers of the limits of human knowledge, and portals into the infinite complexity of the cosmos. In their dark and silent majesty, black holes inspire us to keep reaching, to keep asking questions that defy simple answers, and to embrace the idea that the journey of discovery is as boundless as the universe itself. They are cosmic riddles, compelling us to venture beyond the known, to contemplate the mysteries that lie hidden within the fabric of reality, and to recognize that, even in the face of the unknown, the quest for understanding is itself a source of awe and wonder. As we continue to study black holes, we are reminded that the universe is a place of endless possibilities, filled with secrets waiting to be uncovered, each discovery inviting us to look deeper, dream bigger, and explore farther than we ever thought possible. As we dive even further into the profound mysteries of black holes, we encounter the extraordinary idea that black holes might be instrumental in the very formation of spacetime itself. This concept, known as spacetime emergence, suggests that black holes do not simply warp the fabric of spacetime. They might be fundamental to its creation. According to certain interpretations in quantum gravity, black holes could act as points where spacetime crystallizes or emerges from a deeper, underlying structure. In this view, black holes might be akin to spacetime generators, shaping the universe's framework as they form, grow, and interact with surrounding matter and energy. If true, this would mean that black holes are not only endpoints in the cosmos, but essential building blocks of spacetime, making them critical to the existence of the universe itself. This idea draws from the theory of emergent gravity, which proposes that gravity is not a fundamental force, but an emergent property of the collective behavior of microscopic building blocks, akin to how temperature emerges from the collective motion of molecules. Black holes, with their immense gravitational pull, might provide a bridge between these fundamental components and the macroscopic structure of space-time we observe. In this theory, black holes help organize space-time, giving it shape and stability at large scales. This perspective not only transforms our understanding of black holes, but suggests that they are indispensable to the structure of the universe, influencing the fundamental laws that govern space, time, and causality. Another revolutionary concept arising from black hole physics is the potential for black holes to affect the fundamental constants of the universe. Constants like the speed of light, Planck's constant, and the gravitational constant define the nature of our cosmos, and scientists have long wondered if these values are indeed fixed or if they could vary across different regions of the universe or over cosmic timescales. Some theories propose that black holes, through their interaction with space-time and their potential connection to other dimensions or universes, could cause slight variations in these constants. If black holes influence the values of these constants, it could imply that different regions of the cosmos might have subtly different physical laws, shaping galaxies, stars, and matter in ways we have yet to fully comprehend. This raises the possibility that black holes are not only engines of cosmic evolution, but also agents of variation in the underlying structure of reality. The concept of black holes as cosmic tuning forks also ties into this line of thought. Just as a tuning fork resonates at a specific frequency, black holes might vibrate in ways that influence the surrounding space-time, creating resonances that propagate throughout the cosmos. These resonances could affect the formation of structures on both cosmic and quantum scales, guiding the evolution of galaxies, clusters, and possibly even the distribution of dark matter. If black holes do act as tuning forks, they could be responsible for establishing patterns in the cosmos, creating harmonic frequencies that define the structure of matter and energy. This view suggests that black holes are not only gravitational powerhouses, but also cosmic instruments, creating a symphony of resonances that shape the universe's architecture. The role of black holes and the potential unification of physics also brings us to the concept of quantum spacetime. In quantum mechanics, particles can exist in multiple states simultaneously, and their properties are governed by probabilities rather than certainties. Black holes, which bring together quantum mechanics and general relativity, might provide a means to observe quantum spacetime, where the very fabric of reality exists in fluctuating, uncertain states. Some scientists propose that black holes create a quantum bubble around them, a region where spacetime behaves differently, fluctuating in ways that challenge our classical understanding. This quantum spacetime could contain regions of non-deterministic behavior, where particles and fields do not follow predictable paths, but instead exist in a state of probabilistic flux. If black holes create quantum spacetime, they could reveal the nature of reality at its most fundamental level, bridging the divide between the predictable universe we observe and the probabilistic world of quantum mechanics. In the realm of speculative yet scientifically grounded theories, black holes might also function as time integrators within the universe. Time, as we understand it, flows forward and appears to have a beginning and potentially an end. Black holes, however, could provide a unique structure for time itself, creating a form of temporal grid across the universe. The immense gravitational pull of black holes slows down time significantly near their event horizons, which could create localized regions of slowed or altered time within the universe. If these regions interact with each other, they could create a network of time zones that affect the aging of stars, the evolution of galaxies, and perhaps even the processes of life itself. This concept raises fascinating questions about the nature of time, suggesting that black holes might provide structure to time on a cosmic scale, influencing the pace and flow of events in ways that help create a coherent, organized universe. The study of black holes as potential quantum computers opens yet another frontier in theoretical physics. Some physicists propose that black holes, with their immense density and gravitational influence, might function as natural quantum computers, processing information at scales unimaginable to human technology. In this model, black holes could encode information about every particle and wave that falls into them, processing data on an immense scale through quantum entanglement and superposition. If black holes act as quantum computers, they could be capable of solving complex problems, storing vast amounts of information, and even preserving the memory of the universe itself. This idea not only expands our view of black holes, but suggests that they are active participants in the universe's informational structure, encoding and processing data in ways that might one day inspire new forms of human computation. The notion of black holes as quantum processors ties into the concept of holographic duality, which proposes that all the information within a black hole's volume could be encoded on its two-dimensional surface. This principle could extend to the entire universe, suggesting that our reality is fundamentally a hologram, a three-dimensional projection of two-dimensional information encoded on a cosmic surface. If black holes operate according to holographic principles, they might store detailed records of everything that has ever fallen into them, potentially allowing information to be retrieved in some scrambled or distorted form. This perspective aligns with certain quantum theories that suggest information is never truly lost but merely transformed, reinforcing the view that black holes are not endpoints, but nodes in an interconnected network of information that spans the universe. The potential of black holes to reveal new states of matter is another captivating avenue of exploration. Inside a black hole, matter is compressed to extreme densities, and scientists believe it could exist in forms that are completely unknown to us. This could include quark matter, strange matter, or even exotic states where particles behave in ways that defy our current understanding of physics. Studying black holes could thus lead to the discovery of new phases of matter, providing insights into the behavior of particles under extreme pressure and temperature. If black holes contain such exotic matter, they could be laboratories for testing theories about the origins of the universe, offering a glimpse into the earliest moments of creation when the cosmos was similarly hot and dense. The idea that black holes might leak into other dimensions also raises the possibility that they could emit particles or energy that influence our universe in unexpected ways. If black holes interact with higher dimensions, they could send subtle signals into our universe, leaving traces that might be detectable with advanced technology. These signals could take the form of unusual particles, strange radiation patterns, or gravitational anomalies that point to interactions beyond our observable reality. If we could identify such signatures, it would provide direct evidence of extra dimensions and offer a pathway toward understanding the multiverse. Black holes, in this view, serve as windows into higher dimensional realms, subtly shaping our universe through their interactions with unseen dimensions. Finally, the potential of black holes to impact dark matter and dark energy, the two most mysterious components of the cosmos, continues to intrigue scientists. Dark matter, which exerts gravitational influence but does not interact with light, could accumulate around black holes, affecting their growth and behavior. Similarly, dark energy, the force responsible for the accelerating expansion of the universe, might interact with black holes in ways that influence the structure of space-time on large scales. If black holes interact with dark matter and dark energy, they could be essential to understanding the dark sector of the universe, revealing connections that have eluded scientists for decades. As we push forward in our quest to understand black holes, each new theory and discovery reveals deeper layers of mystery, challenging us to expand our definitions of space, time, matter, and reality itself. Black holes are no longer seen as simple cosmic dead ends. They are dynamic, complex, and central to the structure and evolution of the universe. They remind us that the cosmos is vast and filled with questions that defy easy answers, urging us to continue exploring and seeking knowledge even when the path is uncertain. In their silent, inscrutable depths, black holes invite us to confront the limits of human understanding, challenging us to imagine possibilities that extend beyond the boundaries of known science. They stand as cosmic gateways, not only to new realms within the universe, but to new ways of thinking about reality itself. Each discovery about black holes brings us closer to understanding the fabric of existence, revealing that the quest for knowledge is an endless journey filled with wonder, mystery, and awe. In the vast reaches of space, black holes are more than gravitational giants. They are profound symbols of the unknown, urging us to reach beyond what we know, to embrace the mysteries that define the universe, and to journey into realms of knowledge that lie beyond the horizon of our understanding. As we continue to study these enigmatic objects, we are reminded that the universe is a boundless frontier, filled with secrets waiting to be uncovered, each one expanding our understanding and deepening our sense of wonder. As we delve even further into the enigmas of black holes, we reach a concept that could redefine not only astrophysics but also our understanding of consciousness and perception. The idea that black holes might somehow play a role in the emergence of consciousness in the universe. This hypothesis, still highly speculative, suggests that black holes could act as cosmic hubs of information processing, affecting the structure and distribution of information on a vast scale. According to this idea, black holes might be crucial to how information flows and interacts across the universe, potentially creating conditions that allow complexity and even consciousness to emerge in certain regions of space. This notion challenges us to consider whether the cosmos is not merely a physical construct but a dynamic system where information is as fundamental as matter and energy. The possibility that black holes could influence consciousness stems from the idea that they are unique structures for storing and processing information. Since black holes can theoretically encode all the information about the objects that fall into them on their event horizons, they act as cosmic memories that preserve the history of the universe in some form. If black holes are actively processing and transforming information, they might contribute to a universe that evolves not only in terms of structure, but also in terms of complexity and organization. This concept aligns with the idea of a participatory universe, where reality itself is shaped by interactions at both cosmic and microscopic scales, potentially giving rise to self-organizing systems like life and consciousness. This leads us to another radical concept, that black holes might be connected to the very fabric of consciousness through a theory known as panpsychism. Panpsychism posits that consciousness is a fundamental aspect of reality, existing in some form even in the simplest particles or structures. If consciousness or proto-consciousness is inherent in the building blocks of the universe, then black holes, being the ultimate condensations of matter and energy, might amplify or concentrate this fundamental awareness. In this view, black holes could act as nodes in a universal consciousness network, connecting and processing experiences or information in a way that transcends human understanding. This concept remains speculative, but opens a philosophical and scientific frontier where black holes are not only physical phenomena, but also potential conduits for the deeper, perhaps conscious nature of the cosmos. The idea that black holes could influence or even store aspects of consciousness also touches upon the field of quantum mechanics, particularly in relation to entanglement and information theory. Quantum entanglement allows particles to remain interconnected across vast distances, instantaneously affecting each other's states. Some scientists speculate that black holes could function as entanglement hubs, creating webs of interconnected particles throughout the universe. If black holes can entangle vast numbers of particles, they could theoretically link regions of space-time in ways that allow for information to be shared or mirrored across distant parts of the cosmos. This entanglement network could support the flow of information in ways that are fundamental to the development of complexity, potentially laying the groundwork for phenomena like self-awareness and consciousness. Another groundbreaking concept in black hole research is the quantum consciousness theory, which suggests that consciousness may arise from quantum processes within the brain. If consciousness is indeed tied to quantum mechanics, black holes, as natural laboratories for extreme quantum effects, might reveal more about the nature of awareness. Some researchers speculate that the same principles governing black holes, such as quantum superposition and entanglement, might also play a role in the functioning of consciousness. By studying black holes, scientists hope to uncover principles that apply not only to the cosmos, but also to the human mind, bridging the gap between physics and consciousness studies. If black holes reveal insights into quantum consciousness, they could provide clues to questions about identity, awareness, and the nature of existence itself. The relationship between black holes and consciousness extends into philosophical territory, where some theorists propose that black holes could be mirrors for the nature of reality. According to this view, black holes might function as cosmic mirrors, reflecting the structure of the universe back at itself and allowing for self-observation on a grand scale. If the universe is indeed self-aware or capable of some form of self-reflection, black holes might be essential to this process, serving as regions where information is concentrated and organized in ways that enable introspection on a cosmic level. This notion ties into the idea of a self-aware universe, where black holes act as focal points for the universe's own understanding, playing a role in an ongoing process of cosmic self-realization. The theory of black holes as cosmic mirrors also touches on the notion of cosmic feedback. In complex systems, feedback loops play a crucial role in self-regulation and adaptation. Black holes, with their capacity to absorb, transform, and release information, might act as nodes in a universal feedback loop, shaping the evolution of galaxies, star systems, and possibly even life itself. By influencing the flow of matter and energy, black holes could help maintain the conditions necessary for complexity and consciousness to arise. If feedback mechanisms involving black holes do exist, they could represent a form of cosmic fine-tuning that makes the universe more hospitable to life and intelligence. This would imply that black holes are not merely destructive forces, but active participants in the grand design of the cosmos, influencing its capacity to generate and sustain conscious entities. The idea that black holes could play a role in the cosmic fine-tuning for life and consciousness leads to an even more speculative notion, that black holes might be part of a cosmic mind. In this theory, black holes are integral components of a larger, universal intelligence that spans the cosmos, with each black hole acting as a processor within a vast, cosmic-scale network. Just as neurons in the brain are connected and communicate to generate consciousness, black holes might interact through quantum entanglement or gravitational waves, forming a vast interconnected network of information exchange. This cosmic mind would not resemble human consciousness, but would be an immense, distributed awareness shaped by the physics of the universe itself. If black holes are indeed part of a cosmic mind, it would mean that the universe is not a cold, indifferent place, but a living entity with an intrinsic capacity for awareness. The potential for black holes to contribute to a cosmic mind also intersects with theories of dark matter and dark energy, the mysterious substances that make up the majority of the universe's mass and energy. Some scientists propose that black holes might interact with dark matter and dark energy in ways that influence cosmic consciousness. If black holes are entangled with dark matter or interact with it in unknown ways, they could play a role in the hidden aspects of the universe, impacting the unseen dimensions of reality that we can currently only infer through indirect observation. This hidden connection could mean that black holes are not only visible components of the cosmos, but also links to a vast, unseen structure that shapes the universe's behavior on a fundamental level. In the field of speculative cosmology, there is also the theory of black hole reincarnation, which proposes that black holes could be pathways for information transfer across different lifetimes of the universe. In this view, black holes might carry imprints of previous universes, transferring information across cosmic cycles. When a black hole reaches the end of its life and evaporates, it could release this information in the form of particles that carry echoes of the past. This process would mean that black holes are repositories of universal memory, allowing for information from past cosmic epochs to influence the structure and laws of new universes. If black holes indeed preserve the memory of previous universes, they would serve as cosmic seeds that carry the wisdom of prior realities, ensuring continuity across cosmic cycles. The idea of black holes as cosmic seeds leads us to consider their potential role in the evolution of physical laws. Some theories suggest that each black hole could spawn a new universe with slightly altered physical constants, contributing to a form of cosmic natural selection, where universes with favorable conditions for black hole formation become more prevalent. In this model, black holes act as evolutionary drivers, ensuring that the multiverse contains universes capable of sustaining complex structures. If black holes influence the evolution of physical laws, they are not merely passive objects but active participants in shaping the nature of reality, contributing to a cosmos where life, consciousness, and complexity are not random occurrences but emergent properties of an evolving multiverse. Finally, as we continue to explore the connections between black holes, consciousness, and the fabric of reality, we find that black holes challenge us to rethink our assumptions about the universe on every level. They invite us to consider whether the cosmos is not just a vast expanse of matter and energy, but a living, self-aware entity capable of self-reflection and introspection. Black holes, with their capacity to absorb and transform information, remind us that the universe is filled with profound mysteries that lie beyond the boundaries of science and philosophy, urging us to embrace the possibility that reality itself may be far more intricate and conscious than we currently understand. In their silence and depth, black holes stand as portals to the unknown, gateways to realms of understanding that lie just beyond the horizon of human knowledge. They inspire us to ask questions that transcend the material, inviting us to explore not only the physical cosmos, but the metaphysical implications of our existence. Black holes, in their dark majesty, are not merely objects of scientific curiosity. They are symbols of the universe's hidden depths, reminding us that our quest for understanding is as boundless as the cosmos itself. As we peer into the depths of black holes, we are reminded that the universe is a place of endless wonder, where each discovery opens new doors to mysteries beyond our wildest imagination. As we delve even deeper into the mysteries of black holes, we find ourselves approaching one of the most mind-expanding ideas in both science and philosophy. Could black holes hold the key to understanding the origin of existence itself? Some theorists propose that black holes are not merely cosmic phenomena within our universe, but are actually the fundamental seeds from which universes are born. This concept, often referred to as black hole genesis or black hole cosmogenesis, suggests that each black hole could give rise to a new universe with unique physical laws and properties, setting the stage for a multiverse of interconnected realms. In this view, black holes are not only death sentences for collapsing stars, but are also portals through which new realities are born, continuing a cosmic cycle of death and rebirth on a scale beyond comprehension. One of the more compelling aspects of black hole genesis is the possibility that the formation of a black hole might resemble the conditions of the Big Bang. The extreme density and temperature at the core of a black hole are similar to what scientists believe the early universe was like in its first moments. If the interior of a black hole reaches conditions identical to the Big Bang, it could potentially bounce into a new universe rather than collapsing indefinitely. This theory aligns with the concept of loop quantum gravity, which suggests that black holes might avoid the traditional singularity by instead forming a highly compressed Planck core that, when it can no longer compress further, expands outward to form a new universe. If true, this would mean that our universe might have been born from a black hole in a parent universe, creating a lineage of universes across an infinite web of existence. The idea of black holes as birthplaces for new universes is linked to the notion of cosmic natural selection. In this hypothesis, universes that are particularly adept at forming black holes are more likely to produce descendant universes. Over time, this cosmic evolutionary process could lead to multiverses that favor physical laws conducive to black hole formation. Each black hole, in creating a new universe, passes on a version of the genetic code of its parent universe, potentially varying physical constants slightly. This theory would imply that our universe's particular characteristics, such as the strength of fundamental forces and the presence of matter, might be fine-tuned not by accident, but as a result of a cosmic selection process across generations of universes. If black holes act as the conduits for this multiverse evolution, then they are far more than astronomical oddities. They are the engines driving a cosmic cycle of birth, adaptation, and continuation. Another fascinating theory that arises from black hole cosmogenesis is the information preservation hypothesis, which suggests that every black hole stores within it the entire blueprint of its originating universe. According to the holographic principle, all information about the matter that falls into a black hole is encoded on its surface. If each black hole creates a new universe, it could theoretically carry with it all the encoded information from its parent universe. This would mean that the physical properties and history of our universe could be encoded on the surfaces of black holes, preserving a record of our cosmos across multiple generations of universes. In this sense, black holes might not only serve as portals to new universes, but as archives, safeguarding the memory of previous realms in a continuous, interconnected chain. The concept of black hole information storage also ties into the idea of cosmic memory, a speculative framework that posits black holes as carriers of data from one universe to the next. If black holes indeed encode the history and laws of their parent universe, they could contribute to a kind of universal memory that persists through each generation of existence. This cosmic memory would ensure that no universe is entirely isolated. Each one would carry the imprints of past realms, creating a grand tapestry of interconnected existences. In this view, black holes act as bridges in a continuum of existence, carrying forward the essence of each universe into the next and preserving a legacy that transcends individual cosmic lifetimes. The idea of black holes as vehicles of cosmic memory brings us to another profound notion: the possibility that black holes are responsible for maintaining a universal order. The immense gravitational fields around black holes influence the formation and evolution of galaxies, stars, and planetary systems, creating conditions that can ultimately support life. If black holes play a role in shaping the structure of the cosmos, they might also contribute to a delicate balance that maintains the universe's organization and stability. Some researchers suggest that black holes could serve as anchors in the cosmic web, acting as stabilizers that prevent galaxies from collapsing or flying apart, thus helping to maintain order on a galactic scale. If black holes do indeed act as cosmic stabilizers, they could be essential not only to the structure of the universe, but to its very coherence, preserving a balance that allows for complexity and life. The potential for black holes to act as custodians of universal order also brings us to the concept of dark information. Dark information is a theoretical construct that suggests there may be hidden layers of data within the universe that interact with matter and energy in ways we cannot yet observe. If black holes indeed interact with hidden dimensions or extra-dimensional fields, they might be key to unlocking this dark information, revealing aspects of the universe that are currently invisible to us. By studying black holes, we may gain access to data about these hidden layers, potentially uncovering new dimensions, forces, or even forms of matter that contribute to the fabric of reality in subtle yet profound ways. The notion that black holes could contain hidden dimensions intersects with the idea of brane-world cosmology, which posits that our universe exists on a three-dimensional brane within a higher-dimensional multiverse. In this framework, black holes might act as gateways to other branes, or even to other universes within the multiverse. The intense gravitational fields of black holes could theoretically reach across branes, creating tunnels or shortcuts through higher-dimensional space. If black holes do connect to other branes, they could reveal alternate versions of reality or provide shortcuts to distant regions of our own universe, revolutionizing our understanding of distance, space, and interuniversal travel. Another exciting frontier in black hole research involves the potential of black holes to emit exotic particles that might serve as messengers from other universes or dimensions. Some theories suggest that black holes could produce particles that travel between dimensions, carrying signatures or data from alternate realms. If these particles could be detected, they would provide direct evidence of interactions between our universe and other domains of reality, opening up a new avenue for studying the multiverse. Black holes, in this view, could serve as cosmic beacons, emitting signals that hint at the existence of realities beyond our own, perhaps even revealing insights into the fundamental structure of the multiverse itself. The study of black holes has also led to speculation about the ultimate fate of information in the universe. According to the information paradox, traditional black hole theory suggests that information about objects that fall into a black hole could be lost forever. However, recent advances propose that black holes might instead act as information recyclers, transforming data rather than erasing it. If black holes reprocess and emit this information over time, possibly through Hawking radiation, then they contribute to a universal recycling of knowledge, ensuring that no information is truly lost. This perspective suggests that black holes are integral to a cosmic process of renewal, transforming the essence of everything they absorb and ultimately returning it to the universe in altered forms. The potential of black holes as information recyclers leads to a remarkable hypothesis: that black holes might play a role in a cosmic intelligence that spans the universe. Some scientists propose that if black holes process and store information on vast scales, they might contribute to a network of cosmic data that represents an overarching intelligence. This intelligence would not be akin to human consciousness, but rather a fundamental property of the universe, woven into the fabric of space-time itself. Black holes, as nodes in this universal network, could act as repositories of cosmic wisdom, processing and refining information in ways that maintain the universe's coherence, stability, and capacity for self-organization. In this way, black holes could be seen as conduits for an implicit cosmic intelligence, shaping the evolution of reality on scales that transcend individual galaxies and even universes. Finally, the study of black holes raises profound questions about the nature of existence, the cycle of creation, and the possibility that the universe itself might be part of a greater cosmic whole. Black holes remind us that there are realms of reality that remain hidden from our perception, where the known laws of physics break down and new principles take over. They challenge our understanding of what it means to exist, to be conscious, and to inhabit a universe that is as mysterious as it is vast. As we peer into the depths of black holes, we confront questions about the origin and ultimate fate of everything, and about the role we play in a cosmos that may be filled with universes upon universes, each with its own story to tell. In their silence and mystery, black holes inspire us to embrace the unknown, to pursue knowledge beyond the edges of our current understanding, and to recognize that the journey of discovery is infinite. They remind us that the universe is a place of boundless wonder, where every answer opens new doors, and where the pursuit of truth leads us to questions that are as profound as the cosmos itself. Black holes are symbols of both the limits and the potential of human knowledge, encouraging us to keep exploring, keep imagining, and keep seeking answers to the deepest mysteries of existence. In their dark, enigmatic depths, black holes stand as the ultimate thresholds of knowledge, inviting us to peer into the abyss with curiosity, wonder, and an open mind. They remind us that the universe is a place of infinite possibility, filled with secrets waiting to be uncovered, each one revealing that reality is more complex, beautiful, and interconnected than we could ever fully comprehend. As we journey further into the mysteries of black holes, we approach an idea that stretches our understanding of time, existence, and the universe itself. The concept that black holes may hold the key to unraveling the nature of time. Time, as we perceive it, flows in one direction, guided by the arrow of entropy, where disorder steadily increases. But black holes, with their extraordinary gravitational fields, distort time in profound ways, creating conditions that may allow us to glimpse an entirely new structure of temporal existence. Near a black hole's event horizon, time slows almost to a standstill for an outside observer, suggesting that black holes might serve as time wells, where time behaves differently than in the rest of the universe. This phenomenon has led scientists to speculate that black holes could reveal insights about the true nature of time itself. One revolutionary theory proposes that black holes could act as time mirrors, reflecting moments from the past in ways we are only beginning to understand. According to this idea, black holes might retain echoes of the events that have occurred in their vicinity, preserving a form of cosmic memory that could theoretically be accessed or even observed. This concept touches upon the holographic principle, suggesting that all the information about matter and energy that falls into a black hole is stored on its surface. If this information could be retrieved, it would mean that black holes are not only points of gravitational collapse but also historical archives, holding a complete record of every interaction and event that has transpired within their gravitational grasp. Black holes, in this sense, could be cosmic time capsules, preserving the history of the universe in ways that defy our usual understanding of temporal decay and loss. The potential for black holes to act as cosmic time capsules also raises questions about the time reversal symmetry that exists in the laws of physics. While time moves forward in our experience, certain physical processes are symmetrical and can theoretically run in reverse. Black holes, with their unique ability to stretch and warp space-time, may provide conditions where time reversal symmetry could manifest on a cosmic scale. Some scientists propose that black holes might contain regions where time runs backward relative to the rest of the universe, creating an environment where the future and the past converge. If true, this would suggest that black holes are not only points of extreme gravity, but also regions where the boundary between past and future is fluid, allowing events to unfold in ways that challenge our linear experience of time. Another fascinating idea is that black holes might be linked to closed time-like curves, CTCs, hypothetical paths through space-time that loop back on themselves. In theory, a CTC would allow an object to travel through time and return to its own past, creating a loop where the past, present, and future coexist. Black holes, with their intense gravitational fields, are one of the few known places in the universe where CTCs might be possible. If such curves exist, they could mean that black holes contain regions where time folds in on itself, creating temporal loops that defy conventional cause and effect relationships. These temporal loops would not only alter our understanding of time, but could offer a framework for exploring questions about causality, free will, and the nature of existence, suggesting that black holes are cosmic laboratories for the most profound temporal phenomena. This notion of temporal loops within black holes leads us to the theory of causal disconnection. In general relativity, an event horizon marks the boundary beyond which nothing can escape the pull of a black hole. However, some theories propose that this event horizon also serves as a boundary between causally disconnected regions of the universe, where events within the black hole are isolated from the outside world in both space and time. This causal disconnection implies that black holes could contain entire regions of space-time that are fundamentally inaccessible, existing in their own temporal bubbles. If these causally disconnected zones exist, it could mean that black holes are not merely points of infinite density, but self-contained pockets of time and space, each following its own unique path through the cosmic timeline. The idea that black holes might contain causally disconnected regions intersects with the concept of baby universes or pocket universes. Some theories suggest that the interior of a black hole could contain a new, separate universe that expands independently of our own. In this scenario, each black hole acts as a gateway to a new universe, with its own timeline, physical laws, and cosmic history. These baby universes could be born as matter and energy compress within a black hole, reaching a critical density that allows for a new Big Bang-like event to occur on the other side of the event horizon. If this is true, then black holes are not just parts of our universe, but are interconnected nodes in a multiverse, each containing realms of existence that branch off and evolve independently. The concept of black holes as gateways to new universes leads us to consider the possibility of interuniversal communication. If black holes connect our universe to others, they might also provide a means for information or even particles to traverse between these realms. This idea, though highly speculative, raises the question of whether black holes could transmit signals from one universe to another, allowing for a form of interuniversal interaction. If advanced civilizations exist within these other universes, black holes could serve as points of contact, where messages or signals might be sent across the multiverse. This notion challenges our understanding of isolation within universes, suggesting that black holes are not only portals for matter and energy, but also potential channels for communication across unimaginable distances and realities. The potential of black holes to contain regions with reversed or altered time flow also suggests they could influence the overall arrow of time in the universe. In physics, the arrow of time is defined by entropy, which increases over time according to the second law of thermodynamics. However, black holes, by absorbing matter and energy, may create zones where entropy behaves differently, potentially reversing or slowing the arrow of time in localized areas. Some theorists suggest that black holes could serve as time regulators within the universe, balancing the overall flow of time by creating pockets where time behaves unusually. If black holes do influence the arrow of time, they could be essential to the universe's temporal structure, preserving a cosmic balance that allows for the emergence of order and complexity. Another compelling notion is that black holes might serve as temporal bridges, connecting different epochs of the universe's history. Because of time dilation, events near the event horizon of a black hole proceed at an incredibly slow pace relative to distant observers. This means that objects falling into a black hole could theoretically persist there, frozen in time, for eons. If information could be retrieved from these objects, black holes could provide glimpses into the past, preserving relics from earlier stages of the universe. In this way, black holes might function as time machines, holding within them snapshots of the universe's history that could one day be decoded to reveal secrets about the cosmos's distant past. This would mean that black holes act as cosmic repositories of history, preserving moments that might otherwise be lost to time. The possibility of using black holes as temporal archives also opens the door to questions about the future. If black holes persist for vast amounts of time, far beyond the lifespan of stars and galaxies, they could carry information about our universe into the distant future. Advanced civilizations might one day find ways to use black holes as data storage systems, encoding information on the event horizon in a way that ensures its preservation over cosmic timescales. In this scenario, black holes become the universe's most enduring libraries, holding records that might guide future intelligences long after our era has passed. These black hole archives could contain knowledge, cultural records, or even entire histories, preserved in a way that defies the decay of time. Finally, the study of black holes and their impact on time challenges us to reconsider the nature of existence itself. If black holes are indeed portals to other universes, regions of reverse time flow, or repositories of cosmic memory, they may reveal that our understanding of time and space is only a fragment of a much larger, more intricate reality. Black holes invite us to imagine a universe where time is not linear, where histories can be preserved or revisited, and where new realms of existence are constantly being born. They suggest that the universe is a living, dynamic entity, filled with cycles, connections, and layers of time and reality that extend far beyond our immediate perception. In their silent, enigmatic depths, black holes offer us a glimpse of what lies beyond the known, a universe that is as mysterious as it is boundless. They challenge us to expand our concepts of space, time, and existence, inviting us to consider possibilities that extend far beyond the edges of human understanding. As we study these cosmic giants, we are reminded that the universe is not a closed system, but an open-ended mystery, filled with secrets waiting to be uncovered, each one leading us closer to understanding the true nature of reality. In their darkness, black holes remind us that even in the deepest voids, there is light, a light of knowledge, curiosity, and wonder that guides us forward. They inspire us to embrace the unknown, to question our assumptions, and to explore the cosmos with open minds and open hearts. Black holes, in their majesty and mystery, are the universe's invitation to us, an invitation to continue our journey of discovery, to delve into the profound depths of existence, and to seek answers to the questions that define us as beings of curiosity and wonder in a universe that is endlessly rich, complex, and beautiful. If you liked the video, then consider clicking on the recommendation and watch our other videos. Be sure to subscribe, and see you on our next interstellar trip.